So this tutorial is a really cool collaboration between 5 different companies. I'll introduce everybody in a minute. And it's really aimed to be at this crossroad of, you have literature on one side, which is very theoretical, a lot of proofs, and quite difficult to figure out how you can apply this and what it means for a practical setting, but also all these blog posts and videos on the other end that are a bit too shallow. They don't really touch the depth that you might need to cover when you work with them in practice. And we've set aside about 3 hours of content, so bear with us, but I think it's going to be a lot of fun. So my name is Bram. I'm in the top left. I work for a company called Booking.com. Europeans might know it. Americans will say, what a small little company is that? My focus is on Bandit Feedback and counterfactual learning and evaluation. So this is really my bread and butter. And I'm joined today with Olivier, who might want to introduce himself for a minute too.
So I work for a company called Research, and I've been working on policy learning for the last 6 years, I think. So yeah, that's really my main focus. Let's say.
So we have Ben London from Amazon. He's in Amazon Music, incredibly knowledgeable about a lot of this stuff. I think he is probably, after the two of us, has made most slides of this tutorial. Then we have Zara, Spotify, a lot of experience in bandits and reinforcement learning. Ying from Netflix. Also, I think she has worked there for about 6 years already. And then Devesh, who is the veteran of the industry. I think we were just discussing that he had been at Netflix for 12 years or so. So someone who has had a lot of experience and worked on this stuff for a long time. So together we were able to get a really nice overview of all the material. So in case you want to follow along, I will hide this floating panel again. You can take a look at our site. That should contain the slides. I think we haven't updated all the last changes, but it should be more or less up to date. We also have some hands-on exercises. They're not really exercises, they're more to follow along. You can find them here, and also links to our profiles in case you have any follow-up questions. So I'll leave this open for like a couple seconds in case. If you need them later, Olivier will probably be happy to share them. So the agenda for today, as I said, it's a 3-hour tutorial, so bear with us, but it's going to be a ton of fun. We'll start with a quick introduction on Bandit Feedback, which I think is essential because that sets the groundwork, the foundations for all of the other topics that we'll discuss. And then next up, I will walk you through on policy bandits. For those who have worked with bandits in any way or form, probably this is what they're familiar with. Most importantly, most commonly discussed is regret minimization, but we'll also spend some time on something called pure expiration, which I think probably many of you are not familiar with, but is a very prominent topic nevertheless. And then we'll get to my favorite part, and which is not just because Olivier is presenting it, but just because I think it's super important, which is off-policy bandits, which is likely the type of bandits you'll use most rather than the one you'll see about most. And then following up on this, we have some practical considerations. These mostly reflect the off-policy setting, but also a bit on the other settings. And these are really things that through trial and error and a lot of failures, we've been able to figure out that this is probably something you need to think about. And then finally, we have 2 more sections on large action spaces, which is very relevant for a lot of our industry practical settings, and rewards, which I think is also not very prominently discussed in Bandit literature usually. So any questions about the agenda or the setup before I dive into the Bandit feedback setting? Perfect. So let's put some foundation in of what we talk about when we talk about bandits or bandit feedback or bandit algorithms. And if you've ever been to a talk where they mention bandits, maybe yesterday, they always show this picture of a slot machine, usually with a big squid pulling all these different arms. And this is because the term bandit comes from the term one-armed bandit, which refers to a slot machine with an arm, and it steals your money. And in the bandit setting, we talk about trying to figure out which one of these slot machines has the highest payout. Because underneath, all of these slot machines are set up by some casino owner to rip you off, with one of the slot machines maybe being a little bit more favorable for you than the others. The problem is we can only pull one of these machines at a time, and we have no information about this optimal slot machine. So how do we get to the optimal slot machine if we can only pull one at a time? And this is a stark contrast to most other machine learning settings where we talk about, well, I wouldn't say most, but very commonly, if you get introduced to machine learning, you talk about full information. You have all of the different labels available. In Bandit Feedback, you don't. You only have whatever you have interacted with. So if you present an action to a user, that's the information you're getting, nothing else. And that's essential to this Bandit Feedback setting. Throughout the tutorial, we'll sometimes refer back to this guiding example. It's a neutral ground for all of the companies. We talk about wildlife preservation, so 3 different ads, videos with different themes, but all in the intention to get people to donate to wildlife preservation. So if you see this, it's about this problem statement that we have invented. We have 3 video ads. We might want to show them on Facebook, and we need to determine which of these is the most effective for us. Let's get back to the Bandit Feedback. So if we talk about the Bandit setting, we tend to talk about a very specific loop, so to speak. And in this setting, we have an environment. If you've ever worked with anything related to reinforcement learning, you might be familiar, but this is the external environment that we interact with. This is the basis for all of our information that we don't control. The environment provides us with context. So for example, these could be features about the time of day, anything about the user, anything about the slot machine, and these are provided to the agent. We are the agent, or at least we control the agent. The environment also provides the available actions. What can you do with the environment? And with these 2, our agent produces a policy. And this policy is it's generally stochastic, but it can also be deterministic, which is just a model that maps the context and available arms to selected actions. We then select an action to present to the environment, and the environment provides us a reward, which is then again, whatever utility we're trying to get from the environment. And in this setting, we try to learn as efficient as possible. And one important thing with the Bandit setting is that this is 1 round. We have 1 round, and that's the only thing we work with. And that brings us to the next slide, where in Bandits, we have a clear assumption that we are stateless. And this sets us apart from reinforcement learning in the sense that we look at the current state of affairs, we make a decision, and we assume that we do not get another opportunity to interact with this environment. So we do interact with the environment again, but not with this particular context. So we're not trying to influence the environment for our future steps. Like we cannot do easy route planning or those kinds of settings. And that sets us apart from the rest of the field of reinforcement learning. We do, however, have the option to make things contextual. And this brings us a little bit closer to this long-term planning, because we can do things like velocity features where we introduce features that do say something about the environment and how it's changing. But in our assumptions, so if we design an algorithm, the assumption is always that it's stateless, which makes it much easier to work with. And although you might think, well, that's a strong assumption, it is something you can really work with also in a practical environment. Also important is that the goal of the Bandit is 2-sided. In industry, we tend to think about reward and utility. That's a thing that we can measure. But if you read a paper on Bandits, they always talk about minimizing regret. And regret is basically the, in hindsight, performance of this system. It's usually used to prove some kinds of bounds on how well this algorithm theoretically performs. And in order to get a measurement of regret, you do need that full information setting. So that means that regret is something that in practice you cannot really use. You can only use it to prove something about the algorithm theoretically. A small thing to mention, and I think then we're getting to the end of the definition setting of the Bandit Feedback, is that we can talk about a very large amount of applications. And there's different scales that you can put these applications on. And just to focus our tutorial for a bit, we can talk about single actions, 1-arm Bandit. We only take 1 action, or we have some combinatorial set of actions. So for example, single action could be an ad placement, like we cover here. But if we would display the ads in a ranking, that would become closer to a combinatorial setting. We show more than one arm. So now we need to reason about a lot of biases in showing more of these arms at the same time. And you can even go one step further where you optimize a whole slate. For example, in Netflix, you have these different boxes with themes, and then within those boxes, they will have videos. You can either treat them separately as separate problems, or you combine them. We also talk about discrete versus continuous. And in all the things we mentioned so far are very discrete. You have one action you can pick that's one out of a list. But you could also think about things like price setting, dynamic pricing, where it's more continuous. You can convert these to a discrete action space by just saying we have a fixed set of options. But in this tutorial, we really focus on the ad placement and ranking setting. They are used, these exact same techniques can be used for the other two, but you need to make some assumptions that we won't really cover here. Just give 1 second for the photos to be made, and then I'll move on. Any questions so far? Because then I'll move on to on policy.
Sorry.
Yeah.
Back to the last slide. Yeah. May I know a little bit more about the difference between the single action and the combination for real? Yeah. For the single action, do you mean that we only select arm at one time state? And for the combinational, do you mean that we select a set of the arms at the same time?
Yeah. So the Bandit feedback really speaks about you don't have full information, but it doesn't mean you can have not more than one arm at a time. So in combinatorial, you take more arms at one time. So yeah, exactly. Cool. Let's move on to on-policy bandits. So one natural way to think about this bandit problem, and I think that's also especially if you read blog posts, they're usually about on-policy bandits, is the following. So in on-policy bandits, the policy interacts directly with the environment. That's why it's on policy. So the environment provides the context, you make a reward, you take an action, you get the reward, you update your policy, and then the cycle continues. And you tend to do this when there's no prior locked data available. So you start fresh, you might have a new banner you want to place, you have no information about how that will interact. That's when you can think about using on-policy bandits. And it's really about this way of efficiently figuring out what type of data you need to explore to figure out more about the environment, and at the same time making as much utility out of this process as possible. The most common way of reasoning about this is regret minimization. And in regret minimization, well, I will give you some example of how regret minimization works. But in regret minimization is really what we just discussed with the Bandit feedback, with the slot machines. You're trying to not regret decisions you've made along the way of optimizing your process. And let's start with a very simple algorithm, right? We want to quickly give you some sneak peek of types of algorithms that can be used here and how that applies. So I would say the simplest algorithm you can use is something called explore then commit. And explore then commit, you might say, well, that's too easy, but it's always good to start with the basics. Let's say we have our setup here. We have a bunch of incoming traffic, people that come onto our site. We have our policy, you can see it as sort of a gatekeeper. We have our available arms, the different ads we could show. And then finally, we get this reward. Did they make a donation, yes or no? And in explore then commit, what we do is we start by exploring all of the arms uniform randomly for a set amount of time. So we set a time frame. We just randomized all our traffic, and we allocate the arms randomly. Then after this set amount of rounds, we measure the conversion of each of these arms, and then we decide which one has the highest empirical mean, and that's now our decision for the rest of our time alive as this policy. You might say, well, this sounds very similar to something like A/B testing. It is. The only big difference is with A/B testing, you have all kinds of significance testing. Here, you're very naive. So it's a very basic method of working. And to visualize this a little bit in terms of the reward over time, so the thing that we're interested in is we have this theoretical optimum, right? We have one arm that is probably going to be the best for all of our donations. And then this is our North Star. This is what we want to achieve. We don't know this. Let's be clear. We don't know this. Then we start with exploration, pure random. So that's probably much lower than this optimal. And then after the exploration rounds, if we did well, we will have a reward that will be parallel to this optimal line. And to come back to the term regret, what we discussed before, is this difference between these two lines you could see as the total regret, but usually we're more interested in that the regret becomes zero at some point. So if you read a paper about regret minimization, it's usually talking about sublinear regret. This regret should become smaller over time. We should be learning. But as I said before, we don't have this information. So if we're in a practical setting and we probably have an algorithm that already has these bounds proved, we're not working with this. So we're looking at the reward and return of this. So we don't know what's the optimal. And this gives us a little bit of a complication with explore then commit, because if we underexplore, so due to noise, we haven't found the optimal, but one of the suboptimal arms, we still get a boost in our reward after we stop exploring, but it's not optimal. So we might make this in a non-optimal choice for the rest of time, which is obviously not a great choice. Now, I would be very, so the regret keeps growing. So I would be very ignorant to not mention epsilon greedy here. I think probably everyone has at least heard the term epsilon greedy at some point. And with epsilon greedy, it's very similar to explore then commit. It's basically a family of explore then commit. In epsilon greedy, we have a fixed percentage of randomized traffic, not just at the beginning, but always on the side. And with epsilon greedy, the greedy part ideally is this optimal line, because at some point we will find the optimal arm. And then our performance will be somewhere between the randomized line and this optimal line moving forward. And depending on how big our epsilon is, we'll get closer to this line, yes or no, and sooner or later. The big problem here, and that's the introduction to what we'll discuss next, is that over time, this epsilon traffic becomes very expensive, right? At some point, you know the right outcome. And at that point, all the epsilon traffic could be considered just waste. But if you set it too low, you might be greedy in the wrong way for too long. So tuning this epsilon parameter is quite difficult and quite challenging.
Excuse me, is the reward here in the part represents the accumulative reward along the timeline, or just a reward at a certain time state?
So probably as a practical, so you're asking if you're interested in the current reward or the accumulating reward. And I would say that usually we're interested in the accumulating reward, right? That's the total cost or total gain. But you might say, well, we're willing to explore for a bit, and then afterwards we want to have a good, stable reward.
I know this is pretty common in the Bandit setting. So I guess maybe the reward here in this plot, maybe the accumulating reward. But in the reinforcement learning community, most people think the reward represents the reward at a certain time state.
Yeah.
Then denote it as the RT, right?
Yes. Well, that's the reward you get at that moment in time, right? Yeah. Yeah. So I would say that you're always, in practice, interested in the reward over the life cycle of your system. Yeah.
Can I ask some questions about this? So in this time, the optimal reward is linear. So is that means that when you make assumptions saying the functional forms of whatever reward you have is linear, or is it always is the same case for non-linear like function?
I think the linear part here is a little bit like it's just a random line. The more important thing, I think, in your question is the question about the shape of the reward, like yes. Is the Bernoulli or normal, and you tend to have to make that assumption in most sets of algorithms. No, the shape of the reward itself, and I think in our tutorial we mostly focus on Bernoulli shape rewards, so click feedback or did they book yes or no, but there's very different approaches to the different types of assumptions on the shape of the reward.
Yes, I mean because in a sense this true optimal reward is the actual reward function, right?
Yeah,
it's supposed to have. So whatever the function forms of this reward function is supposed to be the optimal line up here.
Yeah, although this is more of the growth of that reward. So obviously in real in reality it would go up and down.
Oracle knows.
Yeah, exactly.
Yeah. I mean, yes. I mean, it's supposed to be based on your assumption as well, like how the function forms of the reward.
Absolutely, but in practice, you never know the optimal line. So you need to make some assumptions about it, and that's how you design the system. And question. So now I've mentioned already that now we have this epsilon parameter, which is quite difficult to work with, or we need to do an explore phase. It's also quite difficult to work with. So the goal of these on-policy algorithms is usually to make that decision for you, or at least make it easy to set up a system that decides what to explore at what point in time. And oh, sorry, I'm skipping ahead of myself. So there's two notes I want to make about this, because it's a bit short-sighted what I just told you. One is that if people actually work with epsilon greedy in reality, they will likely decay the epsilon over time. So it's not really continuous exploration all the way through. And also epsilon traffic. So this epsilon piece of randomization is something that is not just used for this learning of a stationary environment, but also just to keep some holdout. So I think almost all the companies that have contributed to this tutorial, they have in many of their systems some form of epsilon traffic, even if they're not necessarily using epsilon greedy as their way of working. So these are very valuable techniques to have in your tool set. Now, as I said, this is very inefficient exploration. It's uniform random. We need to pick some level of exploration that's very difficult to reason about, especially if we don't have this ground truth. So can we do better than just this uniform random exploration with a fixed set of traffic? And there's a ton of algorithms. I think the two most commonly known are UCB, upper confidence bound, and Thompson sampling. We'll just cover UCB just because I think it's a very visual way of going through this type of principle. But if you really want to try something out, you'll have to do a little bit of research yourself. So the way UCB works, the upper confidence bound algorithm, is it converts all of these different arms into confidence intervals. And these are, to your question, shaped, like they're motivated by your assumption on the shape of the reward. And now what we do, well, this is, I think, the most basic form of UCB. There's specific ones for Bernoulli, specific ones for all kinds of applications, but this, I think, is the most basic, very easy to implement. And what you do is you control the confidence bound by some confidence parameter. So that's really based on your appetite for risk. And then you act optimistic. You just pick the arm with the highest current confidence. You're just saying, whatever has the most potential within my risk tolerance, let's go with that first. And as the estimates converge, non-optimal arms are pulled less because they're allowed to have a bigger confidence interval than the more optimal arms. And at some point, this will converge to just pulling the best arm without having to tune this complicated epsilon parameter. There's this nice video. This is actually a Thompson sampling algorithm, but the principles are the same, where you can see this, how this visualized, right? So if we play this video, you'll see that all these arms are competing. They're all being pulled separately. There's one arm, the blue one, that is the best. The others are all the same. And at some point, the blue one is getting ahead. And from that moment on, it's just blue, 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 maybe a little bit of the other ones, depending on how the confidence bounds are at any point in time. So here you don't have to really think about what's my decay, what's my epsilon. You just need to define your risk appetite, which is a great way of working. Now, this is all under the assumption that you use no context. So you just assume that everybody wants to have the same ads. And you can enrich with context. For example, I can imagine that the average surfer would be more interested in coral reefs than in polar bears. So we need to try and find these types of methods for personalization, contextualization. There's two reasons why we want to go contextual. The first one, I think, is quite obvious. That's because adding user context, for example, allows you to do personalization. You can learn which actions are best for particular users under certain user characteristics. And many of these things are contextual, right? But there is one that's a little less obvious. We won't cover it in the next couple of slides, but a little bit later. And that is that if you had context for the arms, you can also improve the scaling of your algorithm. Because, for example, in the case of booking, we have millions of hotels, but they all have a price. And that price can have shared learnings between these hotels, so it can allow you to not just pull every hotel once to learn from the hotel, but share these learnings. So as I said, this is especially important when your action space scales. So for 3 ads, probably not that important, but the bigger this amount becomes, the more important. The simplest way of adding context is something called one bandit per context. And you'd be surprised to see how often this is actually used. And the way one bandit per context works is any algorithm we just described. Previously, you had one policy. But instead, now we create one bandit per discrete set of contexts. So basically, if we say, for example, surfers, if we know that the interest is surfing, we might create a separate bandit for all our surfing traffic, let it converge separately, get specific optimal arms for that chunk of traffic. And then for, let's say, people that are known to be in a relationship, they might like the cute little polar bears. Those would be more important for them. The nice thing about this is it's extremely easy to implement. That's why it's still being used, right? If you have, for example, in regulations, you're not allowed to do a lot with pricing personalization. So you might only have a few brackets. And this could be just fine. And it works very well if you have these low cardinality features because you have plenty of traffic, you can do this. But there's no shared learnings. And as soon as you get higher cardinality or continuous features, this breaks down and you cannot really move forward. So I just want to briefly mention this, but one way of improving this is to add some form of regression to your bandits. And it sounds very complicated, but generally it boils down to having, for example, decision tree or regression or neural network. You can use any type of underlying technology as long as it can estimate some kind of mean and some kind of uncertainty that you can use to then guide this exploration. And for example, in the case of linear UCB, you just need to have some algorithm that can give you an upper bound. And in this case, the paper that is mentioned here below, that's the linear UCB paper that converts UCB to a linear method. It's just a simple linear regression, but I've seen many deep learning approaches doing something similar. One way, if you want to try this out, there's a package called VoBoRabbit. People love it, people hate it. I'm on the verge, but this is a very common way that people actually go for on-policy learning with a lot of these techniques that are already embedded there. It's also, I think it's created by Yahoo Labs and John Langford, who's like one of the big names in Bandits. He contributed to this, so it's something with a bit of a a resume. On regression bandits, it's great because now you can get these high cardinality features. It also works with larger action spaces because you can now embed these action features, but it's not trivial to optimize. So that's why one bandit per context is still used quite a bit, is because if you don't need it, this is probably going to be much harder to work with. So you really need to figure out if this is a trade-off you want to make. Now, we've talked about on-policy, and we've said that you need to interact with your environment. So you might be thinking, well, that makes a bit of a complication in terms of evaluation. Because if you want to do on-policy learning, you likely will need to also optimize with real users. So inherently, you need to evaluate with real users. So you require first a warm-up period. If you run an A/B test, for example, you will first need to warm up because otherwise you're going to lose anyway because you did a lot of experiments. And then you need to run your experiment. So that's quite a long life cycle to go through if you want to use this with real users. And hyperparameter tuning becomes a pain real quick. But there are also offline methods to do this. There's a method called replay, where you basically use uniform random traffic or some bias corrected traffic to try and reproduce whatever the on-policy method would do. Not really optimal. I see a question in the back. Explode and commit. So in A/B testing, your goal is usually to measure, so to hypothesis testing. So you want to have some level of significance. With explode and commit, it's really about decision making. So you might be willing to, and there might be way more arms. Like you might do explode and commit with 10 different arms. With A/B testing, it's usually 1 or 2. But the big difference is really this significance testing and this meticulous. One of the big problems with replay is that you need to pick an action, and if that action is not available, you just skip it. You go to the next one. So you need an abundance of data available, which is quite expensive, especially if you have a lot of arms. So that's why it's not optimal to use this, but it's a way to get things going. And the simulation is definitely not an evaluation method. It's just a way to validate your assumptions on your algorithm to the best of your ability. So these are rough estimates for sure. Yeah.
If in the extreme case, if we allow an unlimited long warm-up period, wouldn't the most simple policy like the explore and commit give the best result?
That's a very good question. So the question is, if I have unlimited budget and I can just do uniform random as long as I want, is that better than anything else I can do? Probably. But it's unbiased. You have an abundance of data. It's probably the best thing you can do. Then I would not even go to the on-policy methods. Like then we would go, I think that's part of your slides as well, is like, if you have logs, then, and they're uniform random, perfect. It's just very expensive and unrealistic that you have enough to actually do something with it. So now we talk about this interactiveness with the environment, right? And that's great if you have a simulation, but in practice, things break up a little bit. So the question is, when do we actually update our policy? And in theory, these updates are synchronous. So for after each interaction, you observe the reward, update your policy, get the next user, and so forth. But this is not really feasible in practice. First of all, the updates are very costly. Like constantly updating your policy is quite expensive. And you cannot really do this because you cannot block your users to go on the website waiting for feedback of the others. So all of the assumptions that are made there generally fall apart quite quickly because you don't get instant rewards. It might take a couple minutes, maybe even hours. Also, it's not really necessary in practice because not every request needs the most up-to-date model. So it might be fine to be suboptimal for a couple minutes while the model's updating, and then you get to a better state. So in practice, most of these systems are updated in batch. I was actually at a workshop yesterday with Minimisation, who was presenting something about Google's system, and they said, we have a real-time system. We update every 15 minutes. Right? So that's considered real-time. That's a very quick update cycle. In Booking, for example, we do have a system that does this real-time updates, but I'm not sure if it's really worth all the investment in infrastructure to build something like that. So, well, nice visualization of batches. The advantage of these batches is that it's much cheaper because now you can bundle them, you can throw them through a GPU instead of having all these updates separately. And updates can be asynchronous. So the load on your system is much lower. So you just accumulate all of your data until you have enough to really have an efficient set of updates. The big question then becomes, how frequently should it update? And that is really something you have to decide depending on the system. So probably at the beginning of your system, you want to update more frequently. If you update every 24 hours and the first 24 hours are random, that's maybe very expensive. But at some point, if your system has converged, you can maybe update every 24 hours or every hour, depending on how your system is designed. This can be quite difficult because I know that a lot of infrastructure and data warehousing and companies only updates data every 24 hours, which is probably too long for on policy, especially at the beginning of your cycle. Yeah, so it can depend on batch sizes. There are, however, a couple very clear advantages of this type of on policy learning. And the most important one is that these type of methods are very turnkey. If you have UCB running, you could have a non-technical user that just says, I want basically the same as an A/B test, say, I want to run this algorithm and I want to figure out which one is best. Just empirically, they can start an experiment with this. It's quite simple. That empowers non-technical users, right? So even if you're a technical user, it's quite quick, but if you're a non-technical user, you could get started with this quite quickly. Also, you don't really have to worry too much about the biasness of your data. Obviously, there are biases that you have to keep in mind, but you don't have the biases that we'll talk about later in off-policy learning, because the systems are in charge of making decisions and inherently ensure that the whole update cycle is unbiased. As I said, in contrast to off-policy learning. But, and this is a very big but, is one thing that people would quickly start adding to this list is also you have an online system so you can adapt to changes. And this is very, very not true. If you have these types of on-policy or online learners, they don't adapt to change by default. You really need to adapt your system to deal with this. There's ways of doing this with like sliding windows over your data, discarding old data, or having importance weights. We won't go into detail because I think you really quickly start getting into problems when you try to do this on a very dynamic environment. And Devesh actually made, that's the second part of the video I showed earlier, where this is actually the one that I showed before, right? So if this environment is stationary, all these arms compete, and now at some point the best arm gets ahead. And just to visualize, I need to wait for this video to finish to go to the next slide. Let's assume we'll go back to our practical example, right? The ads, and now suddenly a new government comes into place or a new policy gets introduced, and all of the values of ads, so sorry, people are willing to spend more on ads, on donations because it became more favorable for them. Then you get into real problems, and I'll show you why. So in this case, we start with the same setup as we had before, but during expiration, suddenly all of the arms became more valuable. And what you see now is that the arm that happened to be ahead at that time, which is in this case the purple one, benefits most from the shift in distribution. And we actually have problems with these types of settings in our on-policy methods. For example, while optimizing, if there is some form of local seasonality, for example, there's more transactions at night, people are more willing to buy things at night, and it could be that whatever was ahead by chance at night will now become the winner. So this is something you have to be really careful with in your assumptions. They might adapt a little bit, but not to the extent that you would really trust them. Any questions on this part of on-policy before I jump into pure expression? How am I on time, by the way? Really good? Perfect. Any questions while we're at it? Cool. So far, we've talked about regret minimization, but there's a flavor of Bandits that is called pure expiration. And these slides were partially created by one of my colleagues who is an absolute expert on this topic. And in pure expiration, we can go back to this slot machine analogy, right? So before, we're visiting the casino. By the way, not a recommendation to do. You lose a lot of money. But let's assume you own a casino. And that might be a good investment. You can make a lot of money, but you figure out that you're not making enough money, and you lost either you haven't never read the menu of your slot machine, so you have no idea how to set, the payout rate, or you just don't know that that's how to do it. You lost maybe the keys or something, but now you want to figure out which of these slot machines you have is the most expensive slot machine, because you want to get it out of circulation, give it to your competitor, and make sure that they start losing money. Now, in this scenario, our objective is to find the most expensive machine as fast as possible, but money, so budget, is not really a problem because you can just get the money back through the slot machine, right? It's really about time. And that is that brings us to the definition of pure expiration. Pure expiration is really when your interest is doing hypothesis testing. So it's really a replacement of A/B testing as we know A/B testing. Now, the reason this is interesting is because I've seen a lot of, especially blog posts, but also poster presentations where people use regret minimization algorithms to do things that they want to do as an A/B test. But there's this whole flavor of research that actually focuses on this. So it's good to be aware of this area. There's two types of pure exploration generally. The first one is called fixed confidence. And this is very similar to A/B testing, right? You have a confidence, so your risk appetite that you're interested in, and then you have infinite amount of time to get to this confidence. That's the assumption. The other is fixed budget. You have a limited amount of budget, and within the budget, you want to make the best possible choice. These are two types of decisions you can make. Also, you can do various types. I think this is also the case with A/B testing generally, but it's nice because with pure exploration, it's easier to expand to more arms because your traffic becomes less expensive. You don't have to do 50-50. Worse arms can be discarded earlier on. This also makes it quite common for example, best arm identification. That's a common thing you do in A/B testing. Just find me the best one. But you can also, for example, tune this to return all arms that are better than control, just anything that beats the current control. You can have epsilon best arms, where you say, I want to have all arms within a certain confidence, or even all arms under a threshold. So I want to deploy a new version of our API. Our assumption is that we don't lose money. We just want to make sure that we don't lose money according to our significant statistic. Within fixed confidence, there's three general flavors. So we can work with confidence intervals, so UCB type methods. There's a Thompson sampling type methods. We won't go into those. And then my favorite is track and stop, which is a completely different flavor than most of the algorithms you see in regret minimization. So real quickly, just to give you an intuition of what these algorithms do and why they're different from regret minimization. And one of the easy algorithms to use here, especially because we introduced UCB, is called LUCB. And LUCB, the L stands for lower. So it's now lower upper confidence bound. And the idea is that you constantly pull your best arm or your empirically best arm with the best contender, and then stop when the confidence intervals don't overlap. So as you see here, we have these different contenders. We compute an upper confidence, so this is the contender. And we have our highest empirical mean, which is our current best. And we keep pulling these two. So every time we take two arms that we want to pull, we pull these, then we compute everything again, we do it again, up until the confidence intervals don't overlap. And then you have your decision. Now, I don't have a slide on this, but one thing that it's a small downside of LUCB versus track and stop. You need to decide your confidence when you start. You cannot adjust it because then your sample complexity, as we call it, so the amount of samples you need to reach a conclusion, is not optimal. Another algorithm, and this is actually my favorite, is track and stop. And what you do with track and stop is you use this information theory principle called optimal proportions. Sound very complex, but it's actually quite easy. It just means that if I know the means of all, like the real means of all of my arms, I can compute how much traffic I should have assigned to all of these arms to make my decision as efficiently as possible. And what track and stop does is it basically says, okay, we assume that our current empirical mean is what we need to do. We play whatever arm is the furthest from the proportion that we think it should have. And we have some base level of exploration just to make sure that arms don't get discarded too early. And the nice thing about this is that you don't have to set your confidence at the beginning. So this will just explore, collect data in the most efficient way to make any conclusion at any moment in time. And you can just keep running and at some point make your decision. But obviously you want to make the decision based on some level of confidence. Good to mention, by the way, with all of these algorithms, these are really algorithms you need to do on policy because otherwise you're not really getting the benefits. You can, of course, do batches, but also here, all of the caveats that I mentioned before still apply. So it's not a trivial thing to implement and just say, oh, this is now the way to go. There goes a lot of work into getting these to run in a practical environment. Finally, there's also the fixed budget. Actually not that difficult, at least the basic algorithm that is most mentioned here. In fixed budget, you have a fixed timeline and you need to make a decision as quickly as possible. And a good example of this is some theme of the week, right? So for example, Spotify has a paper last year where they talked about finding the top 10 podcasts every week. And now you have a fixed budget because you only have so much traffic in a week. And now you need to make a decision. And what the method that is most commonly used here is some form of sequential halving. And sequential halving is super simple. Similar to explode and commit, you just sample uniform random. But now at some point in time, usually you need to beforehand determine how much budget you think you'll have. So how many times do I need to halve my traffic to get to the amount of decisions I want? You just discard 50% of your arms that have the lowest empirical mean. You might not even be able to sample all your arms. You just throw away what you haven't sampled. And then you keep doing that until at the end of your budget, you have made a decision. But there's no guarantee that this is the best decision, but it's the best guess you could have made within the time frame. So this is very fast in identifying promising arm, but there's no guarantee on actually finding it. So to get back to this overall on-policy topic, the question is, when does on-policy make sense? Well, it makes sense if there's no prior data available, and we need to be efficient about collecting this data. We also can do this if the cost of making suboptimal predictions is acceptable. So it's not always acceptable to make random choices. So sometimes, so in that case, you probably want to do something else. But that's something that would work for on-policy learning. Also, if you're trying to replace on-policy, if you're trying to replace A/B testing with something like pure exploration, then also it makes sense to do it on policy and not off policy, which we'll discuss in a second. However, there are some clear disadvantages of on policy. First of all, it requires very robust and scalable infrastructure. This is not something you as a single contributor would build just to optimize something. You really need a team of engineers probably to help support this infrastructure. Also, your models need to be able to perform online updates, which is not a given for all of the machine learning models that you can just pull off the shelf. Like, it's really incremental updates, and you need to make sure that there's no bias coming from that. Also, you get slower experimental velocity. You might think that deployments are fast, what I mentioned before, right? You just say, give me UCB, give me this confidence level, let's go. But if you want to test hyperparameters, you have to do it on live traffic. So you can only do so many experiments, and traffic is quite expensive. And for example, if you've done a Bandit algorithm, you've optimized it, and now you want to do a new one, likely you'll start fresh, or you need to figure out some way without adding bias to warm start it. So that makes you quite slow in iterating. And also, this ties into the same topic. Your deployments tend to be blind. You throw them out, you have some intuition about maybe what you've done in simulation or replay, but you have no idea how it's going to respond to the end users, which means that you can get some very wacky UX in that sense. And finally, discuss this as well, but they're very difficult to evaluate offline. So it's not something trivial to do. So that brings us to the end of the on-policy section. Do we have any questions on this part before we move on?
Maybe the Spotify.
Yeah.
Yeah. So, like, how about like trying like have like on making decision on Wednesday, like try something like that to compare with.
So your question is just reducing the budget even further?
Like, oh, you put that, then make decisions instead of this.
I'm trying to make sure I understand the question. So you have a limited budget, and why would you then? Okay, I understand now. So you say it just exploring all the arms and then taking, well, the problem with that is that if you have a lot of arms, you cannot possibly explore them well enough, all of them. So you get very unreliable, very noisy decisions. So what you're basically saying with this algorithm is, I prefer that decisions I make have some basis. So I want to have, for those arms, more traffic. So I rather discard early on and then use my traffic more efficiently. Because maybe you have, I don't know, 10 million podcasts and 1 million users. Now, that's going to be difficult to then explore by Wednesday. But also, if you have 100 million podcasts and 1 million users, yeah, then every podcast has 10 users. That's not a very good proof that that's good. So then you rather have some podcasts that maybe have 1,000 or.
This sort of makes it clear where the bandits are applicable in terms of sort of you have discrete choices.
Yeah.
But what if your choices are not discrete?
Yeah, then this is not an option. If they're not discrete, as for example with something like dynamic pricing, you tend to have to discretize the options to do this. Yeah.
This work in contextual bandits settings. So I know it can be generalized to contextual settings, but does it usually work?
The sequential halving?
Yeah.
Yeah. Yeah. In general, the pure exploration type bandits are not contextual. You could make it contextual, but then you really quickly go to a setting where you would probably want to do regret minimization instead.
Yeah, but that's for one specific context, you can still discard half of the arms.
Yeah, but then, as I said, you get to the one bandit per context setting, and then you will have to have a very limited amount of context, and then you really quickly get, like, you're already at a fixed budget, so you already have identified that you cannot explore everything. So then doing one bandit per context will likely reduce the budget even more. So I think that's not a very realistic scenario that you would try and contextualize it.
All right. Yeah. So the next part of the talk, I think it'll be around an hour, but we'll have like a break for coffee in the middle, is about using everything like really sort of off policy, which I think in general, and I'm very, very biased, but I think in general, this is the more sort of practical part of the talk, because like this is really something that we have all used very often when actually running these systems online, because you have a very expensive cost of engineering to actually get things working sort of on policy. Whereas when you're doing things off policy, things become a lot more scalable, I would say, but also slightly more hard in theory, maybe. So I will go through this maybe a bit faster in the beginning, but really, when things are not clear, please feel free to stop me, and I'll be happy to answer any questions. So exactly, we have talked about sort of these methods so far that are really on policy, where we assume that the policy is going to take a certain action, is going to observe a reward, and then it's able to do like a policy update sort of at that moment. Like that is always the main assumption that you have in these very nice papers that prove bounds on the convergence rate of the sort of cumulative regrets. Like all of these things, they always assume that you can do this like sort of model updating when you've taken an action. That is not a realistic assumption when you're building a system like this, right? And so what we more typically would actually like to do instead of learning for each sample is to use logged data, essentially. And so like when we have logged data just from a week or a month of like just the system that has been really running in production, we can sort of leverage this. And so we will, so like we will have a certain policy that's working in like sort of production, the policy that's choosing the actions that we're logging, but it's not the same policy as the one that we're learning. And so that's why it's called off policy very often. And so here we might have a log where, you know, we have maybe like rows are certain contexts, the different columns are certain arms, and we may have observed certain rewards, like a 1 when the sort of context in that action pair actually led to a reward. And so this sounds very easy, right? Because now we just have a data set, and we know how to work with data sets, right? But the problem here is that this is really only the data that you have are only the sort of factual outcomes. So you know the rewards for the actions that you actually have taken, but you don't know what would have happened for the actions that you did not take, right? And so that really is a big, big problem, that really often we just have no idea what would have happened. And so this this really sort of ties back to the sort of bandit feedback setting, where we don't have supervised learning data where you would just have a full table, but we only have this like a few samples per row here, essentially. All right, and so one of the main things that we try to answer in this field of like sort of off-policy learning, or is that we essentially try to answer sort of counterfactual questions. So, for example, what would the reward have been that this new policy pi would have gotten when that would have been the policy that I would have had in production instead of my logging policy by null? And so the main thing that you have to see here, like the main problem that we have to deal with, is the fact that pi and pi null are not the same policies. And so we need to somehow address the fact that there's a mismatch in the distribution over actions that we're getting from these policies. And so we want to estimate like a certain reward expectation when actions are being sampled from this pi, but we don't have samples from pi. We only have samples from pi naught. And so how will we actually be able to do that? And so this is really something that happens quite often. And I think one of the main use cases for this is when you're doing sort of offline evaluation, right? So in very broad application areas, we have a certain system in production. We want to figure out whether we should be pushing for like a new model class, for example, and we want to know whether this new model class is actually going to do better, and figure out like, when we have maybe like a few dozen options, which ones will make their way to an A/B test. Yes.
Saying like, for instance, I run say Minimisation algorithm, and then I want to know what would happen if I run.
Not exactly. So, I mean, I think maybe more general, you would have a fixed policy. So when you're doing something like LinUCB, you're essentially doing an update to your policy each and every time. Here, we would now have this pi essentially just gives like a probability of distribution over arms that would be fixed. And we're essentially doing this in like a batch setting, where we want to figure out from the policy we have what's a better policy. And it's more like that. So it's a fixed probability. Yeah, essentially.
It is though that the logging policy could be LinUCB. That could be anything, but the read policy, the evaluation policy, tends to be something that is off policy, but doesn't update like. So you could imagine you have your code still running in LinUCB, and then once you want a new one, then you would use it.
Fair enough. Yeah, exactly.
Do you think that there are some difference between the word off policy and the offline? I mean, when talking about the reinforcement learning, we have the on policy, off policy. We also have the online and the offline.
Right. I mean, I think it boils down to semantics. So, I mean, I think when people talk about off policy reinforcement learning, I think you talk about this batch learning from Bandit Feedback. So you do an update, but it's not on policy sort of after every sample. But for example, you do an update once every day, and then you move slowly. When they talk about offline reinforcement learning, I think they assume you don't do an update. So you have a data set, you learn a policy, that's the policy that you are going to deploy, and you never do any updates. I think that's what they mean when they say offline versus off policy RL. But I know like the lines are blurred sort of at times. And so we'll mostly be talking about systems that like you do still want to do updates, but there will be maybe a long time between them. So like maybe once a day, you want to do like a policy update, and you want to figure out what is the policy that is going to do better given my data. Like that's essentially the main question.
Off policy Bandit, learning. So do you mean that we still don't have access to the online environment? I mean, we just have the offline data set and have no access to the online environment.
Yes, exactly. Yeah, like it's purely gonna focus on log data essentially, right? And so like what's really at the heart of doing off policy like sort of estimation or learning is having an off policy sort of estimator. And so now there's a little bit of math, but it's all very straightforward. So we're going to call pi a conditional probability, distribution over actions when you have a certain context. And so that's really just going to be this pi of a given x is when we know like certain information, that is going to tell us how likely we should be to sample certain actions and maybe how unlikely we should be to sample different actions. And so we're going to assume that we now have a certain data set, d null, which has been logged under the logging policy pi null, really just like logged contexts, logged actions, and logged like so rewards. We have these data sets, and so we want a certain estimator, which is v. It's going to take in this data set d null. It has a certain policy pi, and we want to get an estimate of what would the reward have been if we have actions sampled under this policy pi. But we never actually put pi into production yet. So that's really the sort of core of how would you go about doing this. And so this is one point where I think many people are like, whoa, wait, like, why are we essentially doing all of this stuff? We have been doing, like, we have many methods for doing offline evaluation, right? So maybe in one very simple example, suppose we have a user as a context, we have to figure out which item to recommend, just very, very basic. We have methods that do this, right? So Bram mentioned the replay method, where you would essentially have uniformly randomly logged actions. And then you really would just be able to say, well, when the actions are sampled under my new policy, like all I have to do is just count how often I got a reward for the actions that my new policy is going to take, right? And so it's really just, it's a sum over your, a sum over your log data, essentially. You just look at where does my new policy match what I did in production, and that's it, right? So we have methods for this. Why do we want to bother with all of this off-policy fancy stuff? I mean, so yes, this works, but it's incredibly, incredibly costly. Like this is not something you would do in production for any reasonably sized action space. Because of this, like you start by taking a log of uniformly random actions. That's a costly thing to do, and we typically don't really, really want to do that. So that's really, really the main reason. Okay, sure, but then, like even not thinking about replay, I mean, think about the offline metrics we have been using for years, right? Like there's decades of research in like doing recommendation. Most of these papers use recall or like a form of DCG, for example. What's wrong with those metrics? I don't think anything is wrong with them, but I'll just walk you through this sort of example. So now to like move towards a ranking setup, like there's going to be a few slight abuses of math notation in the slides to make it simple. But so now we're not going to show like a single action, but like the action is going to be to show like a certain ranking, essentially, a ranking of different ads. And so I'm going to say that pi null of x and a is going to be the rank of a in the output, right? So for the surfer, like the rank is going to be 3, essentially. And so why do we not just use something like DCG to do like an offline evaluation of the policy pi, right? So let's break down what that means, right? So when we talk about something like DCG, like it's a function, it takes in a log data set, it looks at a certain policy. And so it's discounted for you know, like we have a certain discount function that is dependent on the rank. It's cumulative, so it's a sum over all of the ranks that you have. You have a certain gain there as well. So essentially, we would just look at what are the actions that we are placing at certain ranks, what's the relevance for those actions, and what's the discount for those actions. And now we just need to figure out, well, what is the relevance and what is this like sort of discount function? So when you think about the discount, the most natural thing to do is to just look at like how likely is a user to actually see an item that I rank here, right? So like the reason that you have this sort of discount is really, if I show something at rank 1000, there's a very, very tiny probability that the user will see it. So maybe I should have a low reward, right? So that's essentially what that is. And so most often people use this 1 over the 2 log of rank plus 1 is like just one example of a discount function that like people have been using for a very, very, very long time. Okay, so that's that. And so now, like the only thing we need is relevance, right? We need to figure out what the relevance is for a context and a certain action. And so generally, like this metric would assume that you have a ground truth relevance. Like you know exactly what the relevance is for every context action pair. We don't have that, right? We have this log data. So we might have clicks, for example, right? So like we logged when users clicked on certain things that we showed, but we show things at certain ranks. And so things that are shown very, very low in the ranking will not get a lot of clicks, but they might be relevant. So one thing that you would normally do here is, debias these clicks. And so you, like one really basic thing to do would just be to like take your logged clicks and divide them by the viewing probability at the logged ranks. I mean, so these are just very quick examples. I'm running through this quite fastly, but it's not the main point that I want to make. It's really just to, like sort of give you some flavor. Okay, so this relevance is now just a logged click divided by the viewing probability at the rank that the logging policy was using. So if you plug this back in to what we had for DCG, we have this function. It's a sum over ranks. It's relevance times discounts, but then relevance is a click divided by a viewing probability. But the discount is our viewing probability. So essentially what's happening is we're taking logged clicks in our data sets and we're reweighting them by the ratio of those two discount functions. So it's essentially saying, well, if the viewing probability that my new policy is going to give for this item is higher than the viewing probability that I had for my old policy, then I'm more likely to get clicks, right? Like if this action is going to be viewed really twice as often and I got 1 click, then I can expect to get 2 clicks, right? Like that's a very, very basic intuition. And so DCG is essentially doing a very specific form of counterfactual estimation. Like this is really something that's called, like we're scoring with we're multiplying with the inverse of the propensity score. So it's called IPS, is a very, very common technique in this field. And so essentially this is doing IPS, right? So I would say there's nothing wrong with using DCG, and there's nothing wrong with using these like very sort of classical offline evaluation metrics, but you need to reason about what you're actually doing, right? So just using clicks and just using 1 over the log of rank plus 1, because that's what people have been doing in like research papers for a very long time, is maybe not the thing you want to do, right? And so what's nice about using off-policy estimation techniques is that like it really gives you a formal framework of reasoning about what it exactly is that we're trying to measure, right? And we can map this to an online metric, right? Because we're just like really looking at clicks, we're reweighting these clicks by how likely they are to occur. And so now we have an offline estimate of a CTR, which is a really common metric that we would use in this sort of online test. All right, we have 5 more minutes before coffee. So I'm just going to peek what the next slides are and whether it's worth going through them. I think it is. So only 5 more minutes until coffee. Right. So at the heart of sort of off-policy evaluation, as I said, are these sort of off-policy estimators, right? And there's a few families. And it's not always that clear which family you should actually choose. But now the most common options are essentially 3 families, and I'll just walk you through the first one before coffee. Right. So the most common one, and I think like when you have a background in supervised learning, the most natural one to think about is using value-based estimators. So in a value-based world, you would essentially choose to like have a model that is going to tell you the reward for a given context action pair. So we have this model sort of R of theta, which can be a neural network, it can be like a linear model, it can be like a tree-based model, but it's essentially like just going to try and predict how likely we are to get a reward when you have a certain context action pair. And so we can just use the log data for this, right? So we have the log data, which is not colored, but then we can use this model to essentially fill in the rest of the matrix, right? And figure out, okay, we think that we're likely to actually get a click here. We think that we're unlikely to actually get a click here. And so now, like, you've boiled down this fancy, like, sort of off-policy world to a simple supervised learning problem. And so when you have this model, sort of R of theta, getting a value-based estimator, so given a data set D null, what is the value that we'll get for a policy pi, becomes very straightforward, because we really just look at, well, what is the action that this policy would take? What is the value that my model is telling me that this action has? And I'll just plug that in and I'll sum those, and that's it.
Where are you going to train?
So you have essentially log data just of like certain contexts and certain actions. And you would then just have a model that regresses over the context to get a prediction for the rewards. So you would learn, for example, that certain types of users and certain types of ads are likely to donate. And you essentially just learn a model for that. Now you have that model, and now you can make predictions about unseen sort of context action pairs. Right. And so, like, that's what's nice about this, right? Because we all have used like this sort of scikit-learn probably at some point. You know, we've used these methods that have been really tried and true for a few decades now. And so it's a very low variance approach. We'll have a single model that is going to output a single prediction, and it tends to work very well. Now, the problem is that it's going to be biased, because this model is not going to be fully truthful, right? It's very, very hard to like really ensure that you have a model that's going to know what's the expectation of reward is for a certain context action pair. And certainly when certain combinations of context and actions are very unlikely to appear in your data.
Sorry. How we consider the estimate? That's all based on that.
Yes, I mean, so you need to have some randomization in your data, right? And so hopefully, like, if your randomization is strong enough, like all sort of context action pairs will have some probability of appearing in your data. And if I then have a huge log, then maybe I can learn a model that's going to give me a decent estimate. But it's always a bit of a gamble. And I think that's one of the problems with like these approaches is there are certain context action pairs that will be very unlikely to appear in your data, right? Like I might just be very unlikely to show like an ad for, I don't know, like a thriller movie to a kid, right? Like these are things that will not appear in my data. So now I'm like, the model essentially has no idea what would happen if you do that. So when we get model predictions for that, they might be bogus, and that's a problem. Yes, I mean, so these are the output of a supervised learning model. It's just that plugging in standard models doesn't work as well as you would like it to work. And so there are some extensions that we will go through later. So I don't have slide numbers, but I guess this one, yeah. So like it's really just we have learned a certain model on log data, and now like it's learned on log data. So like it's supervised but learned on Bandit feedback. So I know a context, an action, and a rewards. The context and the action are the input to my model. The reward is the output. And I learn a model that, for example, minimizes like the log loss, for example. And now I just have that model. And now I'm using that model as a counterfactual estimator. So now, like when I try to fill in, you know, what will happen if I show this ad to like this guy, that's the input to my model. And this sort of orange 0 is the output of my model. Like what I just said, we can use value-based methods that are using these supervised learning techniques. It's great in some sense because you can reuse a lot of existing work, works really well, but bias is often really going to be an issue, right? So maybe we can just do better, right? And then like the main thing that I will talk about now, and I think the main thing that I at least have been using very often in the last years is using policy-based estimators. And so there was a very nice tutorial by Jutta Saito and Thorsten Joachims at Rexis 21, and I think also at KDD last year. And so I was rewatching the video, and now like I'm going to quote like a sentence from Thorsten, who said he was quoting Vapnik essentially about like, don't solve a problem by first trying to solve a harder problem. And like this really stuck with me, right? Because exactly like we're trying to estimate this model, like R theta, that's going to give us like a decent estimate for the entire sort of context action space, right? We want to know the exact mean reward for all of the possible sort of context and actions. But that's a very, very difficult problem in like any realistic setting. And we don't actually want that, right? We really just want to have a system that's like an off-policy estimator that's going to give us decent sort of estimates for the model costs and the policies that we care about. And that's not the entire space. That's just, you know, maybe the policies that are close to the policy that we know that we're just really trying to improve upon. And so we can do something simpler, actually. It might not look simpler because we're not used to these things and we like using supervised learning, but it's actually not that hard. The only thing that we're now going to require is that we have a stochastic learning policy. So we need to have a certain non-zero probability of having some randomness in our system. And so the main term that you see in this sort of class of methods is really sort of IPS. And so essentially what you're doing when you're doing IPS is you really just look at, well, how much more or less likely is this new policy that I'm trying to evaluate, like how much more likely is it to do actions that led to rewards in my training data? And so this is like essentially in the example of DCG that I was giving, it was, you know, looking at logged rewards, logged clicks, and looking at how much more likely is a user to view it. That's essentially what we're doing here, right? So what you do here is you have your value of the policy given a certain data set. It's a sum over all of your data. You look at the logged rewards, and you look at, well, what is what is the like sort of probability for this action under the new policy, sort of over what is the like sort of probability under the old policy. And so if this is a very large number, it means that a certain action that did well in your training data, you're going to do more often, and so like it should receive more weight. If this is a very small number, it means that a certain action that was likely under your logging policy is now going to be unlikely, and it should be downweighted. And so I essentially just talked you through what we have now. Very nice visuals, really thanks to Bram. So you look at the logged rewards that you actually have from the logging policy. You then look at, well, how likely was this action to be taken by my logging policy, which is something that you might know because you're the one running the system, right? Like you can just log these probabilities as you're taking these actions. So you have this data. Now you have your new policy, and you also know, like, it's a policy you learned, you know how likely it is to do certain things. So you have all of the information that's needed to actually give you this like sort of unbiased estimate of the reward. And so that's great. It's sort of unbiased, which is very nice in theory, but in practice, it's not always that great, to be honest, because being unbiased is always going to come at a cost of high variance. And variance is a problem when you don't have huge data sets and when you have large action spaces, essentially. And so there will be more focus on that in the very near future. But so, yeah, I mean, it's very nice to be unbiased, but variance can be a problem still in some cases. So we have these value-based estimators, we have these sort of policy-based estimators, and of course, some very smart people have thought about making these work like sort of together in tandem. And then the family that does that are called doubly robust estimators. And so they're doubly robust because like they will provably be unbiased if either your inverse propensity scores that you logged are sort of unbiased, so true, or if your model for the reward is unbiased. Like when that's the case, then you have now a system that's unbiased. And so that's nice, right? Like you're allowed to make some mistakes, like just not like mistakes everywhere, right? But if your model for the reward is somewhat off, or you have somewhat like maybe wrongly logged propensities, it's actually going to work better. And so this is the most math heavy slide. So it's very good that like we all had some coffee, but it's still not that hard. So like I'll really just walk you through it. But so like what you're doing with like a W robust estimate is, so again, it's a function that takes in a policy and a data set, right? And so the value estimate that you'll get here is, as a baseline, it's using the direct method. So that is, you sum over all of the actions, you look at how likely is an action to occur under my new, how likely is an action to occur under my new policy, and what is the reward that I think I will get from doing this action in this logs context, according to my model, right? But then we're also using these inverse propensity scores, and we're using them as a certain correction, right? So this is really just, again, like this ratio of how much more likely is an action under the new policy, if you compare it to the logging policy. But we're going to weight the IPS sort of contribution by the error that you get from the direct method. And so we'll look essentially at log data. We look at the like sort of prediction that we have. And so if my model for the reward is entirely correct, then this will always be 0. So there will be no sort of contribution for IPS. We're just using DM, which is great because the model is really doing well. Now, if my reward model is very bad, for example, like suppose it just is going to output 0, like essentially everywhere, then that means that the contribution of this last term will be 0. You will have 0 here, so this will just be the reward, and then it's the reward times the IPS correction, which is just like the original sort of policy-based estimator. So it's really like a certain type of like mix of the two that works really well in practice. But I must say there's no sort of guarantee. So it's unbiased, you have lower variance when both your model for reward and your sort of IPS model have a reasonable variance. So this is a very vague term. I mean, there's many research papers out there that will give you bounds and everything. But so sometimes your model for reward might be good, but you'll have such high variance in these propensity scores that you're better off just using DM and not looking at this method, because it's really just going to make matters worse, or vice versa, right? Like it really often happens that using IPS actually works better than using like a W robust method, because it's just very hard to get this model here to get that working right. Okay, so that's that. So now I've been talking about doing off policy. Yes. Right. I mean, that's a good question. So we actually didn't really say that. So like sort of pi null is your logging policy. So that's the system that you have in production. And so, I mean, I think many people always make this assumption in papers, but it's not that sort of trivial in practice. But so you essentially make the assumption that we do some randomization and we know what's the logging probabilities for every action that we can take. And we actually log that probability, and it's now a part of our data, and we can use it. In some cases, that's easy. In some cases, it's really not. And Bram will be talking about some of those in the near future. But then, like the sort of pi null is the system we have in production. Pi is a new policy. And so the new policy is just the new system that we have. And so like here, actually, pi can be fully deterministic. And then it's just 1 for the action that matches and 0 otherwise. But often, like you may want to have a model that's, for example, learning like a neural network with like a softmax at the end. So you will learn like a certain probability for like the entire action space. That's how you would get that. And so the main parts now have been about using these off-policy sort of estimators, essentially for like these sort of offline evaluation purposes. But we can also move towards learning, right? And so like when we look at the options that you have for sort of off-policy evaluation, you have the direct methods. It's biased, but there's very low variance. We can use things like IPS, which is unbiased in theory, but have very high variance. We can use things like sort of W robust, which are sort of unbiased in theory, have medium variance. Like it really depends on the case that you're in. And so when we're moving towards learning, we don't really care anymore about getting very decent estimates. But we really just want to figure out like, what do I need to do with my system? Like, what is the policy that I should be deploying in production to actually get a higher reward really right now? And so these off-policy estimators that I have been talking about are essentially like any other metric, right? Like when we think about something like a sort of classification problem, you have log loss, and that is going to be your evaluation metric, but it's also going to be the loss function for your model that you're going to learn, right? When we think about things like regression, you have root mean squared error. Like that's the metric that you're using for evaluation, but it's also what you're using to compute your gradients when you're actually doing model updates. And so this is just exactly the same thing, right? And like this is really like a click that I made in my head that really blew my mind, essentially. Like we always talk about off-policy evaluation and learning as if they're two entirely separate fields, but they're not. Like you need a single estimator, it gives you an estimate. But if it's fully like sort of differentiable, you can just do like steps in gradient descent on that estimator, and now you can learn a policy that's really going to do better. The only difference is that when you're talking about evaluation, you want to have an estimator that's good at approximating this expectation. And when we're learning, we're going to want a certain policy in a certain class of policies that's then going to maximize this sort of estimator. And so it's the same, but not entirely, right? It's like two sides of the same coin, because there are slightly different nuances, right? When you're doing evaluation, you want to have really accurate estimates, maybe over the entire space of policies. Whereas when we're learning, like I just want a policy that's better. And that's not necessarily the same question. Yeah. And so one sort of problem that you have in off-policy learning is that you really start to suffer from something called sort of Goodhart's law, which like I think the original phrasing was something like of any statistical regularity will start to collapse when some pressure is exerted upon it for control purposes. It's like very, very vague mathy language. Then there's like a paper like a few years later that says, well, like a metric ceases to be a good metric when it becomes a target, which I think really makes much more sense, right? So you have this metric, it might give you decent estimates over the space of all policies, but it might be off in some places, right? Like sometimes it might get an underestimate for the value of a policy. Sometimes it might give an overestimate. And so the problem is that like when you're now doing gradient descent on that, you'll find those bumps where it's actually giving a slight faulty estimate, and it's an overestimate essentially. So that's essentially what we talk about when we're talking about sort of Goodhart's law. Right, so when can things go wrong? I think this is my favorite part, because I think knowing when things work is very interesting, but very often things won't work. And so just knowing where the faults are is really something that I always find very interesting. And we'll start with value-based estimators for that. So we have this model for the reward, this R theta. It's going to be, hopefully, like if we have a decent model, we assume that it's going to be very accurate for the complex action pairs that we have in our training data, but the ones where we have loads of, right? So that's really just the sort of actions that were taken very often by the logging policy. We'll have loads of data for those, and we'll be able to actually get very decent estimates for those. But when there's certain complex action pairs that just don't appear in the training data because the logging policy thought that it might be a bad action, we don't really know how to get an estimate for that, right? We have very, very high uncertainty, essentially. And so, like, what's going to happen when my new policy is going to take actions that my logging policy would never have taken? That's essentially the main problem in all of this field, essentially. And so one problem that you have and that you essentially cannot not have is that of this sort of drifting your covariates. And so I'll just walk you through a very simple example with just a very simple plot where we have certain actions, they have certain feature values, and they have a certain outcome. And so we have a log data set with some samples, and this is just my data, right? So I see that I've taken a few actions, and I see that the actions that have higher feature values, they seem to have higher sort of outcomes, right? So this is my data set. I learn a model for the rewards. I'll take a simple sort of linear model. This is great. Okay, so this is my new model now. Now I'm learning. So I'm using this model to figure out what my policy should be doing in the future. I'm seeing, well, higher feature values lead to higher higher feature values lead to much higher outcomes. So, you know, this is the space that I should be focusing on. That's great. So I do that. I get new samples, and they look like this. Okay, so I now have new samples. No problem. I'll just learn a model on that data, and now it looks like this, right? And so I have two models that are entirely like sort of contradicting. Like they couldn't be more contradicting, essentially, right? And why is that the case? And like the reason is just that the sort of distribution of the feature values has entirely shifted. But that's because the feature values depend on the actions. The actions depend on the policy, and that's exactly what we're changing. So this is always going to happen to some extent. And when you have a model that is going to underfit the true data, this is not something that you're going to be able to avoid. So I think in theory, the way to deal with this is to be very principled, to have a Bayesian model with like very good, very good, like sort of estimates of the uncertainty that you would have, because then you wouldn't just have a line here that blasts off into infinity, but you would have a very wide posterior saying, well, like, I just don't know what happens here. And so maybe we can reason about that. That's what I would say in theory, but in practice, these methods are always extremely expensive to compute and also not great. So it's really just something to be aware of when you're working with the sort of direct method. Right. So that's an issue, mostly an issue when models are actually sort of underfitting. So be Bayesian and we're fine. But there's a few more problems, and the problem is called the optimizer's curse, which is a very daunting name, I think, for a stats thing, essentially. But so, like, think about just a very simple setting where we have a value-based policy. It's called pi. It's deciding on its actions via a certain model R of theta, right? So this R of theta is essentially giving a certain estimate for the reward we'll get for a certain context action pair. And so when there's a new context in my system, I'm just going to do like an argmax over all of the predictions to figure out what it is that I should be doing, right? Like this is, I think, very standard. Most real-world systems actually have this running in production, right? And so let's make a very reasonable assumption that this model is not perfect. It's going to have zero mean Gaussian noise on its estimate. I think that's actually not a reasonable assumption to think that you have a model that has zero mean noise. But still, you know, this looks like a very standard setting. And so, like, the sort of main question here is whether there's anything wrong with this setup. Is doing this argmax the best thing you can do? And it's actually quite subtle. So we should expect to be disappointed even if our models are unbiased. Like that's what the optimizer's curse states. Like, why is that the case? Like we are just like, we essentially just get an estimate for all of the possible actions. We take the action with the highest estimate. What's wrong with that? Well, let me show you. So now we'll have a very simple example. No ads for like any donations or anything, just a coin flip. So suppose that I flip a coin and I do it 5 times and I get 4 heads and 1 tails. Now, what is going to be the heads probability for flipping this coin, right? I think most of you will probably say, well, it's 4 out of 5. That's what my data is telling me. And so when you do that, you essentially, like in the background, you have a certain model of what is happening. You have a certain likelihood function, and you say, well, no, I'm reasonably certain it's around 0.8, but it might as well be 0.79 or 0.79 or 0.81. I'm fairly certain it's not 0.1, but there is some likelihood that it actually might be, right? And so when you have to give a single number, you're giving the maximum likelihood estimate, which is this point at 0.8, right? But there's still fairly large uncertainty. And so when we think about this uncertainty as being like a certain Gaussian, and we have a few different actions, so it's essentially like we're sampling a few times from a Gaussian distribution. And so the mean of that Gaussian is 0, but the maximum of those 3 samples is not expected to be 0, right? So for 3 standard, for 3 standard normal like sort of Gaussians, you actually have an expectation of 0.85. And so when you have more and more samples from that same Gaussian distribution and you look at the maximum, that expected value is going to go up and up and up. And so that's why, like, even if like all of your samples have an expected value of 0, they have an expected error of 0, because they're only looking at the maximal one, you don't have an expected error of 0, but you actually have like an expected error that's quite high. And so there's this very, very nice paper that I would strongly like to recommend, where, you know, it shows in like a very standard setting with like a standard Gaussian, when you have 10 different sort of arms and you pull, like, sorry, when you have one Gaussian, you pull, like you sample it sort of 10 times, the expected value for the maximum is 1.54 already. And so now when you have different arms with different estimates that are quite close to each other, there's a very, very high probability that you will be slightly disappointed by the estimate that you get, but also that you'll actually pick the wrong one when you're looking at the maximal ones. But of course, when they move further and further and further apart, then you are less likely to be strongly disappointed and more likely to choose the right one. Okay, so that's nice, but let's sort of bring it back to the example with the coin flip, right? So we should expect to be disappointed even if the model is unbiased, even if we have like a nice, like, sort of maximum likelihood estimate. So we had this maximum likelihood estimate. This is something you can do, but I think it's not the best thing you can do. Many people have thought about this already, and I think it's the entire like sort of cornerstone of doing Bayesian statistics is, well, we don't have a lot of data to base our estimate on, so we use some information to guide us when we don't have any data. And so we might have a certain prior that says, well, if there's no data, then like the main assumption that I have is that the sort of coin is fair and there's a 0.5 heads probability. And so now we can use like a certain really fancy model to get not just a likelihood function, but incorporate a prior. So we get a posterior. And then you have the map estimate that might say, well, it's actually closer to 0.75. But this is still too high. So this is now a slightly better estimate. It's slightly lower, right? So we should expect to be less like sort of disappointed. But it might still be really too much. And so we proposed, like in a paper like a few years ago now, to go one step further and really look at the quantiles of the posterior. So having a lower confidence bound essentially on the estimate in this like sort of off policy world. And so you would have like a certain parameter alpha that you can tune to figure out, well, now like this sort of alpha is the sort of area of the shaded region. And so if I would have a very narrow posterior, then I would have, for the same value of alpha, a very small penalty. But if there's a very wide posterior, then I will have a very large penalty. So you really are essentially sort of penalizing large variance, and you're being very like sort of pessimistic about what you're, sorry, you're being very like sort of pessimistic about what you're trying to like sort of estimate. And I think that that's very interesting, because when we think about sort of on-policy bandits, we always talk about UCB and how it provably pays off to think about optimism, because we will just take the action that has the highest UCB. We'll get more data. So when we're being overly optimistic, that's actually fine because we'll learn that relatively quickly. But in this setting where I just need to learn a single policy, I don't want to be too optimistic, right? And so I should be very like sort of pessimistic instead, which I think is nice, right? So that's what goes wrong when you think about sort of policy, about value-based estimators. I'm going to quickly look how I'm doing on time. I think I'm reasonable. Okay, so what can go wrong when you think about a policy-based estimator? And it's essentially things go wrong in the same settings, right? Things go wrong when your new policy and your logging policy are very, very dissimilar. And what that means is that your new policy is going to be taking actions that were very unlikely to happen in your training data, which means that this logging policy is going to be a very, very small number, right? Because you were very, very unlikely to actually do this, but you got some rewards. And so the weights that you're actually using in your estimator are going to blow up, right? It's really, really a very, very big issue. And that's not a problem when we have like sort of infinite samples, because this is in theory a fully unbiased estimator. And that's great, but I've never been in a situation where I have a data set that's really fully infinite, right? So it's nice in theory, but it doesn't help me actually in like sort of any way. And so to really drive home the point, so really think of a system where we have a 1% CTR, for example. We're doing very simple logging policy. It tries to figure out what the best action is, but then for 0.01% of traffic, I'm going to do pure randomization. We have like 1 billion samples a day and 1 million arms, right? Like this actually sounds like a real world system to me. This is reasonable. So now what this means is that when we're looking at the logging propensity for the exploration traffic, it's going to be 0.01. For 0.01% of traffic, we're going to randomly choose one of those 1 million arms. So this means that your log propensity will be 10 to the power minus 10, which is a very, very small number. So now suppose that we did this well, right? So we're doing this logging. We have a certain action A star that got a click. And we're now going to use this method to actually try and get a reasonable estimates for the CTR we would get under a new policy that is always going to take A star, right? And so what happens when you write out the math is, well, it's a sum over all of your data points. You look at the logged rewards. What is the logging probability for this action? What is the new probability, what is the logging probability? What is the new probability under the learned policy, which will be 0 for many actions. But for A star, it's going to be 1, right? Because that's just what this new policy does. And so essentially, we're dividing by 10 to the power minus 10th. So we get this insanely huge number. Whereas we have a fully unbiased estimator, but somehow my method is telling me that based on a data set with like 10 to the 9 samples, I think somehow that this method is going to give me 10 to the 10th clicks. That's not reasonable whatsoever, I would say, but that's what you're getting. And so clearly we're doing something wrong, right? Clearly we're somehow getting like a certain overestimate here. So maybe we should be slightly like sort of pessimistic with what we're doing. And that's essentially what people have been doing for a long time now. So it's something called clipped IPS. And it's essentially, if something looks too good to be true, it probably is too good to be true. And so like you would essentially just say that, well, you know, this ratio is all very nice, but like when it looks very, very large, I'm just going to cap it. And, you know, like it's like really essentially saying, if my data tells me that this new policy is going to give me like maybe 10 times as much clicks, then I'm willing to believe it. But if it tells me that I'll get like 1 million times as many clicks, I'm not going to believe it, and I'll just leave it at 10 because that sounds reasonable. That's essentially what you're doing here. And now you have a biased method, but you will have much lower variance. And so being biased is not always a big problem. Like lower variance is essentially in these cases very often something you want to do. And so, like, yeah, when you would do this clipping with m equal to 100, then you would get 100 as the output, which is much more reasonable. But it's somehow relatively hard to tune this as a hyperparameter, which can be an issue in some cases. Okay, right. So we can use this clipping to have a bias variance trade-off. Great. Do any other sort of problems remain? And the answer is yes, sadly. So now think of that same system where we have 1% CTR, but I want to try something new. Maybe I don't want to maximize the number of clicks, but I want to somehow use my data to minimize the number of non-clicks that I'm getting, right? Which is essentially the same thing, but it's just a different framing. And so when we try to do that, think of a logging policy that's very unlikely to take a certain action A star, right? And so it's so unlikely that the logging policy is going to take this action. There's not a 0 probability. It's just there's a small non-zero probability, and my log data just does not contain this action. Now, when you're going to take a policy that is going to always take A star, it's going to be optimal with respect to your estimator. And so this is relatively easy to see because you want to minimize non-click. So we'll say that we have a -1 reward for a non-click, and you want to minimize that. Well, if we entirely miss the data, then I just get 0, and it's no non-clicks, and that's essentially what you need, right? So this is a problem that you have as well with these estimators. And what this actually means is that like you can get sort of optimal performance by entirely avoiding your data, which is not something that you want. There's many really nice papers about this on using SNPs, which is called self-normalized IPS. So like it's really about you're essentially overfitting to the propensities by your logging policy, right? Like some actions that were just very unlikely to happen, you're going to focus on those way too much. And it's solved by introducing a sort of control variant, which we will talk about a bit more in the following section. But so essentially, you have the normal sort of estimate for IPS, but you're now going to divide by the sum of the importance weights. And so what would happen in the example that I had is you would have a 1 here for a very low value here. So this would essentially become a very big number. You're dividing by a very big number, so you would get a very low estimate. And so when you're learning, you will be heavily disincentivized to learn policies that are going to avoid your data, because this number is going to be very far from 1, and it's not something you want. You will have lower variance. It's no longer fully unbiased, but this is a method that many people really use very often because there's no hyperparameters, right? You have a really nice trade-off between bias and variance, and you don't have to do anything for it, right? Like there's no weird things that we need to tune. And so this really is very often a sort of go-to method when you're doing off-policy evaluation. Now, when we talk about learning, things become slightly harder. And the main reason is that now we have an estimate that's no longer a single sum over your samples, right? Like this first sum, but we're dividing by a second sum over the samples, which means that when you're doing deep learning, for example, when you're just doing mini-batch optimization, this no longer works because you need to always divide by the full sum over all the samples. And there's some very nice papers that solve this that I link to here, but I won't go into them into too much detail. Actually, I think I will, but very shortly. The main thing is that like the main sort of idea in this paper is to rephrase this as a constrained optimization problem. So you're still trying to optimize the IPS estimator, but you want this value in the denominator to be 1 essentially. You can rephrase this with a sort of Lagrange multiplier, and that boils down to having a certain translation of the reward, right? So like the thing that I was saying about like minimizing non-clicks, and you would have -1 for non-click and then 0 for a click. Like if you actually shift those numbers around, then that example no longer works, right? So we need to somehow learn a shift on the reward that is going to make this work better. And it's very like sort of closely related to baselining in reinforcement learning, which is also done very often to have lower variance on the estimates, right? Like looking at how much better is this action than a baseline action instead of having a single model that's going to have an estimate for the entire reward space because it might be more of an issue. Right. So when we talk about fixing problems in off-policy bandits, I think it's very interesting to me that like for all of those years, I think for the last 2 decades, when we think about bandits, we think about UCB, we think about being very optimistic in the face of uncertainty, right? Because we won't be it for too long because we just learned from it, right? Like we will take certain actions that are being sort of overestimated, but then we learn from that data and we'll never do it for too long. Whereas in off-policy, that's not the case at all. And so very nearly, I mean, I might say all, but I will be wrong probably, but like 90% of the work in this space is really just focusing on being like maybe sort of slightly pessimistic because the data is essentially all that we have, and we have to stick with what we know, and there's no value in doing any type of exploration when the goal is just to get a higher reward, right? Like you might want to have some exploration traffic to learn from decently, but there's no use in being optimistic, essentially. And so when we talk about like sort of being pessimistic, generally the goal is to keep your logging policy and your newly learned policy close to each other. But like, what does close mean? And there's just like a few examples here of how you might think in like a mathematical framework of having policies that are close, right? So we can think about low sort of KL divergence, which is essentially what people have been doing in reinforcement learning, I think since 2015, essentially. So this was a method that essentially does this in like so reinforcement learning, right? Like you learn a policy over time and you want your newly learned policy to be relatively close to your old policy, because then the estimate that you get for the rewards will be much, much better. We can also just think about sort of clipping the importance weights, right? We do this here. When you do that, you have something called PPO, which was also a huge step in the field of RL. I think it's being used in ChatGPT's reinforcement learning from human feedback, actually. So that's essentially this method. Or just, you know, we might just want to avoid the actions that have very high variance and very high uncertainty. That's a very recent paper that works really well. So, I mean, like there's all of these like sort of parallels between methods that work well in Bandits and methods that work well in reinforcement learning. This was the sort of off-policy section. Next, Bram is going to talk about some practical considerations that are not solely focused on the off-policy setting, but I think slightly at least, because we all just really like this setting, and I think it's where most things can go wrong.
So we're going to a slightly different gear now. So far, we've really talked about sort of foundational concepts. So the Bandit feedback, on policy, off policy. We've talked about where things can go wrong, which is, it's very practical, but it's also a bit theoretical. But with this last section, not last section, there's two more coming, but this section, we're largely focused on practical consideration more in a system design type of setting. I can hear feedback though. Is that you? Okay, perfect. So this part is, I think, largely made by Devesh and Ben, who are also in the call. So if you have any comments or I make any mistakes, feel free to drop in. But I will keep going for now. So first of all, and I think this is one of the places the areas that I'm currently working on a lot, which is the data collection for off policy. So Olivier has mentioned that in off policy, we have to make some assumptions about the data being stochastic to a certain level in order to make these counterfactual estimates. And except in very rare cases, this is really a requirement. You need to have some randomized data in order to get your off-policy methods working. You can leverage your current production policy for this, but probably you need to add some randomization. So if you have, I think there was a question in the back, like, can it be LinUCB, for example? If you have something like LinUCB, you might already have some randomization. But if it's just a machine learning model or some business rules, you maybe not. So then you need to add randomization to that. So the big question is, how do we randomize and how do we motivate this? So the first technique, and we've already briefly discussed this all the way in the beginning, is you can just simply apply epsilon gradient. So very similar to what I mentioned before, just with a probability of 1 minus epsilon, we take a production policy. And otherwise, for the epsilon percentage of traffic, we do uniform random. It's also something that Olivier used in this example to motivate clipped IPS, for example. There's also a formula here that's more for references later on, but I think it's pretty straightforward. There's some clear advantages here. It's extremely simple. Honestly, we use this all the time. I know that more people that contribute to this tutorial also have, like, this is something that it works, right? Also, and this is something that's commonly overlooked, it has guaranteed expiration because everything has a guaranteed probability to be explored, which is not a given for the other techniques. However, uniform random selections are very costly, especially if, for example, there's a big difference between the quality of different arms. So it's not something you necessarily want to do without thinking about it a little bit more carefully. Also, and this is also something we've mentioned all the way at the beginning, is that it's quite difficult to tune this epsilon. Like, how much do I need to explore? Because you don't know anything about your data, so you don't know how much you should explore. So that's difficult, especially if you also have all kinds of competing objectives. You want to make enough money out of the policy, but you also want to learn more for later. So this is a difficult trade-off.
I know a little bit about the purpose of the randomization technique here. I mean, why would you randomize the data?
Randomize, you said? Why you need randomized data? Well, that is because if you don't, then you always take one out of the actions, which means that you have no counterfactual of what would have happened if you had taken the other actions.
Yes, so you start from the counterfactual learning paradigm policy, right?
Yeah, it forms the basis of all of the techniques that we discussed in off-policy learning, because there you need to have some evidence of the counterfactual, and this provides it. Yeah.
So in my opinion, this part is for to help the contextual learning. I mean, the learning reward model better.
To learn a better model. That's if this ensures that you learn a better model. That's what you're asking.
Yeah. I mean, this such kind of random data is for learning the reward model better. Compared with such, if we set the data with some production policy.
Yeah, so it's both for learning, being able to learn a better reward later on, but it's also to have better data for evaluating whatever new policy you want to deploy later. So it has a dual purpose. Yeah. So epsilon greedy doesn't get much easier than this. There's also a technique called softmax, or it's also commonly referred to as Boltzmann exploration. And with Boltzmann exploration, you assume that you have a production policy that outputs some sort of score. And now you are going to act proportionally to this score. So you apply a softmax to these scores. There's a temperature, so you can determine how aggressive you want to explore versus how aggressive you want to use your greedy policy. And this way, you are expecting to act more often with your high quality actions. The actions that are a little bit less quality are still explored quite a bit, but the really bad ones are very little exploration. The the good things about this is that now you have this proportionality to your scores. So if your production policy is good, you reduce the harm to your user experience. However, without modification, this does not guarantee that all your arms are explored. There might be arms that are getting a score of 0 by your model, or very low scores, and therefore do not get any exploration at all. So that's a risk. Like there might be areas that are underexplored. And also, just like epsilon greedy, tuning this exploration parameter is not trivial. Like it's not easy to say, oh, I need to do this much exploration to get the information I need, versus I can only afford this much exploration to get the cost down. So, like any good technique, you just combine both the best worlds. So you can also do softmax with epsilon greedy. And what you do here is the softmax or Boltzmann strategy is on the non-epsilon traffic, and the epsilon traffic is still uniform random. So the good thing about this is you get the best of both worlds, you get guaranteed exploration, and you have reduced harm to the UX, given that, of course, your epsilon is lower now than you would have done in just pure epsilon. But now you have two parameters to tune. So pick your poison, I guess. There's not a real clear answer which one is best. It really depends on how well you're able to investigate what works for you. Now, this was really about this one arm. We select one item, we show one item, we determine whether we show that item or something else. But we've talked in the beginning about rankings, and that's a very prominent part of this whole bandit setting as well. And randomization and ranking is slightly different. So we can apply full randomization to a small subset of our rankings, just using epsilon or softmax. Also, if we want to do something like Boltzmann or softmax exploration, we can consider using Blackett loose to be a little bit more efficient, because all of this type of sampling for softmax exploration can be quite expensive if you need to sample like a longer ranking. So you use the Gumbel noise tricks to do this. The problem here is that then it becomes much more tricky to compute the marginals because of all of these different levels of exploration that happen. It becomes quite complicated. Another thing you can do, and this, on the next slide, I'll have another comment on this, is instead of having a full random or the whole ranking being randomized in some way or form, is randomizing subsets. So actually, when I think Google yesterday had also had a talk where they just had the 4th and the 8th position that they randomized for exploration. That's something that you can do too. So either you swap the first position with some random other one. So the ranking overall is quite good, just the first one is bad, or you swap K with another random K, so the second with another. So you just sample 2 positions, you swap them, or you swap always one with the next one. So you swap in those positions. And there's a reason why this is something you can do in ranking and not necessarily something you would think about with one arm. And that is because in ranking, you're not just interested in the propensities as we've discussed before, but you're also very much interested in these positional effects. So you might actually show all items in some way or form, but it's more important where they're shown for example, IPS, than that they are shown. So now you can estimate these position types of biases, so position bias or trust bias, based on just these more elegant randomization than just a full random ranking, which will have less influence on the user experience. And then this is, I think, currently one of my favorite papers of all time. If you want to estimate these position related biases, you can also make use of existing randomizations such as A/B tests to harvest interventions. So in this paper, they say, because you already do randomization in your rankings, wherever your rankings disagree, those could be seen as interventions. And then there are all kind of weighting schemes to correct for certain biases in that sense. And you can get very accurate estimates of these position related biases without actually forcing exploration. So on the ranking space, to summarize this all, is there's a lot more opportunity to do randomization that is different from this one arm, because you can leverage the structure in which you're representing your recommendations, your items. So we've talked about randomization. Now we know a little bit about how we randomize, but now maybe even more importantly, what do we actually log? What do we need to store in order to be able to do all these techniques? And because we're getting a bit tired of lists, let's do it in a JSON format. First of all, very obvious, we need to log the context. I don't think we need to spend much time, but just you need to know what context was used for this prediction. But what is a little bit less trivial to think about if you start with these systems is you also need to understand what the available actions were at the time of the recommendation. In theory, we always talk about we have 3 ads, but in practice, we can maybe only show 2 for demographic restrictions or GDPR, or some things are not available. So it might be that only a subset of arms actually available for this particular user. So we need to know which ones were available, and we'll get to this a little bit more later on because there's more complexities in this part. We also need to know which actions were selected, and maybe even more so, it would be nice to know which actions would be selected, like what's the order of the actions. And also what the reward was we observed for this particular action. Could be a click, or it could be a continuous value, but we need to log this. And then maybe most importantly, and this is something that a lot of systems don't have by default, is we need to know the propensity. And I want to emphasize here, the propensity is not the model score. So I remember that we have a serving system and we have model scores, but the models are deterministic. So then the propensity is 1, not the model score. So you need to log this separately. Now, and this is a thing you have to also keep in mind, is that this is also related to the propensity. We need to encapsulate the entire decision-making process into this policy object. So it's easy to think we have a model, but there might be a lot of elements to the decision-making process that determine how we can use this data later on. In the case of epsilon greedy, it's quite straightforward. You have the epsilon greedy algorithm. We make a decision, how much epsilon, how much not epsilon, and then we have a pure exploit and a pure an epsilon explorer area, and those combined determine what the propensities are. So this whole policy object determines what the propensity is. Quite simple for epsilon greedy, but if you, for example, bootstrap a bunch of policies together, so you might have multiple policies running. For example, 5% of your traffic gets a certain policy, another 5% another policy, and that's just part of your system. Now you want to know for your logging data how much the propensity would be for each of these systems. So you need to combine all of these together to make maximum use of the data that you're producing. Also not unimportant is that you likely want to be able to have this encapsulated system be available offline, so that you can take an artifact. So for example, just some URI in your infrastructure, or the artifact you can download. Just if you have new logs coming in, you can evaluate what this policy would have done. And that also means that you need to make this whole thing reproducible. So likely you would use some form of a pseudo-random number generator based on, for example, visitor ID, that ensures that when you go over the system again offline, you will get the same results. So otherwise you get all of these inconsistencies that are hard to recover. So one thing that is important to note is that we talked about logging propensities, but I just told you that a lot of our systems, for example, don't have propensities necessarily logged. And especially if you have an aggregate of a lot of systems, that might be quite tough to get. So if you don't have propensities, you can also estimate them. For example, you can use Monte Carlo approximation. So if you have this logging policy, you can just sample from this logging policy. So that's a nice thing to have if you have this artifact available, and you can use some Monte Carlo approximation to then estimate the propensities. And this works well when you have no or limited context and just count. Sorry, that's not what I was trying to say. If you have no or limited context, you could even just count the occurrences of all of the different actions you took, because then you don't even need to go for Monte Carlo approximation. Finally, you can also learn the logging policy. And in this case, you can just simply fit a probabilistic model to the actions of your logging policy. And instead of predicting the reward, you predict which action it would take. And actually, arguably, these estimated propensities could even be better than the log propensities. It's not completely clear how they stack up in practice, but you could argue that this reduces variance because you actually take an average of your whole data set rather than this point estimate. Especially if you, for example, keep updating your policy, you might have very different propensities each time you update your policy, but then the whole data set combined, if you estimate the propensity of that, would reduce the variance of the switching of these policies. One thing, and there's also in the hands-on exercises, there's one like 3-line snippet where we estimate the propensities. This is a little bit of a brain breaker. I don't know what's the right word for that, but when you fit a model, you want to do train to test split, you want to be meticulous about it, but when you do propensity estimation, you actually do some form of overfitting. So you don't have, so if you have a training set and a test set for your policy, and now you need the propensities, then you train a separate model for the training set and a separate model for the test set, and you just use those. You don't really have a way of evaluating them. So it's a little bit different than a regular supervised model. So in some sense, you're allowed to overfit because that overfitting is just a little bit taking the averages of the propensities. So we have propensities, we have our system, we have some randomization. So now we deploy a new policy. And this comes back to when I talked about the available actions. In practice, you don't always control the full system. So if there's a downstream system that, for example, applies additional business rules, or it fails altogether, there might be a difference between the intended treatments and the actual treatment. And this little figure demonstrates this. For example, if I have a recommender system that tries to recommend these ads, now I call my policy gives me an ad to show. Then it goes back to the recommender system, and that might say, well, is that ad still available? Because maybe we already hit our donation limit. And then it says no, So it takes it out and it actually takes a second action. And this is way more common than you think. For example, if you have availability of something, like let's say you have Amazon, you have products, you might do search over all the products, but then by the time you make your recommendation, you have a smaller set, and then you can actually, for that set, realistically call the availability of the products. Then there still might be products that are removed from the ranking later on. And this really screws up your ability to understand the propensities because your system is not in control anymore. So in general, if this happens, what you can do, and it really depends on how the system is set up, if the probability to treat, given the context and the intention to treat, does not really change, then you can simply compute the treatment propensities. So the intention to treat rather than the actual treatment. But if you get to a point, and alternatively, you can maybe get these business rules to actually be embedded in your system. But by the time you get to this problem, likely that's not possible because it's too much of a dynamic system. Sorry, I thought it was one more line, but if that assumption does not hold, you will just get into a world of problems, and you'll likely have to figure out a way to disentangle these two decision-making processes because it can be quite complex. Another thing, and this is something quite important, is that if we have randomization, you might cause inconsistent experience to users. So not just randomized means bad, but also if you, for example, show a list of donations and now you refresh the page and you end up getting randomization and the list is different, then as a user, you probably instantly distrust this ranking because why is it suddenly completely different? So a way to solve this is a lot of these systems, they have some form of a cache. So similarly based on the randomization hash that we talked before, so that you can make consistent predictions, you can either use that random pseudo-random number generator or cache in between the policy that if this particular session has already gotten a prediction, we just serve it again. But one important thing here, and that's the lead into the next section, is you need to make sure that you then don't count this prediction multiple times. So if you do a refresh, that you suddenly have someone refreshing the page 50 times, that now suddenly that has 50 samples of something that was purchased. So you need to deduplicate them. Great. Randomization. We have propensities. We have log data. We have the right amount of information. Do we have usable data now? Can we start using these techniques that we have discussed all this time? Well, these techniques are only as good as the underlying data that it uses. And we need to have an understanding of when data is good, which is not always trivial to answer. If we can compute, sorry, what means data is good? It means that we can compute these unbiased estimates of the expected reward. That's what we mean when it's good. Determining that is difficult, right? Because if we knew that, if we knew how to do that, we didn't have to require all these techniques. This unbiasedness is crucial for the avoiding surprise in production. So we really want to have this in the right way. So ideally, we'd also be able to do this before we go to production. So the question is, how can these estimates become biased? And specifically, IPS is quite nice to reason about. Is, for example, if the logging policy isn't random enough in certain contexts, we can never give a good unbiased estimate. This is exactly what Olivier also mentioned before. For example, one way that this could happen, other than just not enough randomization, is that, for example, we have a pseudo-random number generator that is not truly random. This could also introduce all kinds of randomness biases. And I forgot the anecdote, but Devesh had a really interesting anecdote, which means that he's never using the Java random number generator ever again, because it ruined a lot of experiments. But these things can be relatively easy to detect if we have access to the logging policy or the full distribution. But if they're not available, we get into other kinds of problems. We can not easily detect this. Another thing is that if the log propensities don't truly reflect the observational probabilities, and this really relates to the interventions or the failures from the system as a whole later on, as I mentioned a couple slides before. So for example, the downstream filtering rules. But also, what I just mentioned, if you refresh the page, this could really affect the truthfulness of the propensities in the system. So if we now suddenly have 50 examples of someone refreshing the page, encountering us 50 different users, that ruins the propensities. And obviously, there's always some possibility of insidious problems that you just don't know. It can just be something that suddenly comes up. We cannot check for this because we don't know what the things are that can go wrong. So there's this really nice technique. Olivier has briefly mentioned it. It's called control variates. And even funnier is that Ben has written a workshop paper last year about this. And then during this tutorial, we were discussing this, and Nivesh said, well, we also have this. And he had some Netflix document where they basically described the same process. So independently, they figured out the same method of checking these types of data consistencies. And the control variates is actually a really, really simple technique, but it's very powerful. We have in the notebooks, the hands-on notebooks, there is one section where we show how it can be used and how it measures without having access to the actual ground truth, how at least not bad the data is. And the way it works is it relies on a statistic where we know the expectation is a known constant. And in this case, what we just do is basically we do IPS, but without the reward. So we just say, what's the our new policy's propensity divided by the propensity of our logging policy. And then what we do is we basically expect that for any target policy, if the data is good, so not the data is good if, but if the data is good, the expectation of the control variate is 1. So we can simply use a statistical test to determine whether the control variate differs from the expected value. And if it's close to 1, we likely have the right data for the job. And this is extremely nice because now if you have this whole system and you have your exploration strategy set up, you can actually reason about the quality of it before going to production, which is something you don't think about in literature, but is really something in industry you need to face. Now, there's a couple of quick checks that might sound trivial, but are very important that we quickly want to run through. So for example, it is extremely important that you check the log data as well. Like you want to make sure that everything makes sense, right? Is the donation amount the right amount? I've had issues in the past in booking where we introduce a new currency and now suddenly that currency is treated as euros. Now you have exploding numbers in your data set, or your selected action is actually not available. It's not an available action. Now probably your system is broken. Or you want to make sure that your policy selects the same actions online as offline, because otherwise you might get very biased evaluations. What is also important is that you have some understanding of the distributional shifts and the distributions in general. So for example, make sure you are monitoring the intention to treat versus the treatment so that you know if there's a big difference, that there's probably something in your system interfering with the ability of your system to use valid propensities. And also look at the shifts in features and rewards over time. And there's many different tests. Like there's a picture of the Mirnov test, which you can use to get some form of measurement from this. One thing that is also interesting is that if the data is not good, for example, we have this whole complex ETL data transformation process. And if you do that in time intervals, so you do it per hour, per day, or per whatever time interval you're using, if you detect problems in an interval, if you assume that there's no drift, you can just ignore that particular chunk of data and just keep going with whatever you have while you're waiting for maintainers, for example, to fix this. So this is a nice property of these kinds of systems. If the propensities, you can just calculate them over whatever data you do have, and that way you can keep going, even if some of your data is bad. Also, something you really need to do if you do off-policy learning, for example, is you want to take a look at how the distribution of your actions has shifted. If there's a very big shift in what kind of actions you're suddenly taking, it could be a signal that things are bad. So it's a good practice to take a look at how the actions shift regardless of the performance of the model. Because if they shift a lot, that might mean that you had some bias underneath that suddenly gave you very wrong expectations. And finally, and this might be the most obvious one, but really make sure that you have a statistical significant effect of your new policy being better than your old policy, that it's not worse, that it's not the same, because that's what all of these exercises are for. And especially if you heard Olivier about being, that off-policy estimates are usually a little bit optimistic. If you don't do these things, you're going to have a bad outcome anyway. But I think this is one of those things that it's just a good note to end this with. So this was a long list of practical considerations. Now we go back to a little bit more large action space and rewards, which are a little bit more fundamental, I would say. But before we go there, are there any questions on this end? So if I understand correctly, your question is, because we don't control it, should we just ignore it and just focus on the things we do control?
Yeah.
So that is more or less the argument here, but the problem becomes difficult when, for example, there's something that you don't control but has a big effect, right? So for example, I've had this at one point, you optimize a model, you evaluate it, you're like, oh my God, I'm so much better than the base. But then you realize that there is some constraint that only some users can get this massive discount, for example, because they're first-time users or something. Your system doesn't know, and now your system thinks you get a lot of reward for these users because you give them discounts, but you were not allowed to give it. So that can be a problematic outcome. You think you're doing well, but you're not. So ideally, you would know if that action is actually something you're allowed to do. If you cannot get rid of it, you then need to model how likely it is that it will be blocked, and then you can correct for it. So you need to have some intuition on, or some knowledge on what that effect is. But it really depends on what you're blocking and how consistent it's being blocked and what the conditions are for it being blocked.
Right. So I am the final thing between you and lunch. So I will go slightly quicker over these last sort of two sections. They are a bit shorter, I think, than the last ones. But the slides will also be made available on the website. So no worries if you're zoning out already because you're very hungry. But so we had this figure in the beginning where we showed like there's many different settings where you might think about using a bandit, and there's many different ways of thinking about, you know, having different actions. And so in some of those cases, you will get to deal with very large action spaces. And so the problem is that things actually become a lot harder when you have to deal with these settings. And so I'll be walking you through some of them. So like a few small examples, just when you're running something like a sort of content recommendation system and you have a very large catalog, think of Netflix or Spotify or like any other streaming system, very, very large catalogs, choosing an action from that catalog gives you a very, very large action space. Now, the problem becomes even worse when you want to give a list of recommendations, right? Because then we need to somehow model the fact that we're taking multiple actions, but taking a subset out of a small set blows up very, very quickly, right? So when you have, for example, a sort of catalog of 20 items, we have to choose 10 out of them. This means that there's 670 billion sort of possible unique actions to choose from, which is a lot, right? Like that's a problem in many cases. When you think about really sort of fully continuous spaces, this also is an issue, right? So we often think about sort of discretization, and it does make life easier, but sometimes there are reasons why you actually want to model something in a fully continuous fashion, but this means that the action space is essentially sort of infinite. Or when you think about multiple like sort of combinations of actions, right? Like sometimes there are two things that you're trying to optimize sort of fully independently, but they might like sort of interact. Like if there's a certain color on your website or a certain font on your website that you want to choose, maybe the best standalone color and the best standalone font go really badly together, right? And like maybe the second best color and the second best font, that combination is maybe the best thing that you can do. But this means that like all of these different things that you're viewing at as you're seeing as sort of independent decision-making problems, you have to model them all together, and this blows up the size of all of the combinations that you have to deal with, and many, many more examples. And so there's a few challenges. I think when we're talking about sort of on-policy bandits, we assume that we have no data prior, right? We just start learning, we do a certain amount of exploration. And so that's really just going to be an issue when you have a huge action space. Even for smart methods, like sort of UCB, you have a very wide like sort of posterior for all of the arms. You want to get it lower for all of the arms. It just means you'll be doing completely random stuff for very, very long, which is not great. So even if that's not the case, choosing which arm to select becomes very, very, very slow, right? So what we do very, very typically is, in a value-based world, we get a certain context, we score like sort of all of the different actions that we have, we take the one with the maximal score, right? Like that's a very, very normal thing to do, and scoring maybe 10 actions and sorting them is really absolutely fine. But when you have more and more actions, doing this for every context that is coming into the system will not work. It's just gonna be too slow. So maybe slightly more like formally is we have a reward model. Again, this R of theta. It's modeling the expected reward for a given like sort of complex action pair. And we select actions by having this argmax. And so like I'm calling this greedy, but it's essentially, it also includes doing UCB or doing something like Thompson sampling or doing something like LCB. It's essentially just the fact that we have to somehow figure out which action has the largest value, which is in general just a very, very hard thing to do. But that's true because we haven't put any restrictions on this model class R theta. And so it actually turns out when you do think about models that are just more efficient to evaluate, there's some nice tricks you can use. So this is something that I think really many people do. So this is, I think, the basis of any real world Rexis, is that you somehow assume to have a linear model. So your model of the reward is now going to be a certain embedding for the context X and a certain embedding for the action, which is this theta A. And you assume that your reward is somehow, so like it says equal here, but it might be better that it like scales with this dot product between the action embedding and the context embedding. Because now when you have to figure out this argmax, you have to do a maximum like sort of inner dot product search. And this is a problem that many, many, many people have been trying to solve in the database community for the last few decades. So there's loads of papers doing this, and there's loads of really nice tools out there that actually help with this. So I know one is like these navigable small worlds. It's like you use graphs in some way. You have great libraries like Spice, I guess, is from Facebook. I think Annoy is from Spotify. Scan is from Google. Like there's many, many like things out there that really just help in doing essentially like an approximate nearest neighbor search on the embedding space. And so that's, I think, in many cases, what really powers like many of those systems. And so it might sound like having a linear model is a strong restriction, but it's not exactly the case, because it's linear at the final layer, because we need to have this dot product. But how you learn these embeddings can still be whichever method you want, right? So you can still have very, very fancy methods like deep learning to get all of these embeddings. And once you have them, you just have to get a dot product. So that's nice. Okay, so that's what you get for an argmax. But then when you have an argmax, it implies that you're choosing your action fully deterministically, right? We often don't want to do that. Yeah. Yes, exactly. Yeah. And so we often don't want to do that. You often want to have some sort of randomization, and using a softmax is often much more like sort of preferable. And so, like, would we be able to make softmax sampling more tractable? And so for that, like, first I should show what's wrong with the softmax, right? So this is a softmax. It's a very basic equation, and it might look like nothing is wrong there, but you have the sum over the entire action space in the denominator of that quantity. And so when you have billions of actions, doing this computation to get a certain propensity when you're going to sample is going to be incredibly expensive to do. And so you don't want to do that, right? And so if we can somehow avoid summing over all of the actions, that's going to make life a lot easier. And so this is like a few ideas that were mentioned in a paper from Google at Wisdom a few years ago. But there's certain approximations to softmaxes that are actually much, much faster to compute. Or we could just not have a softmax over the entire action space, but for example, say, well, we first get, using an argmax, the top 1,000, for example, and then have a softmax over those 1,000 items and randomize over that subset of the data, which already will work reasonably well. And so when you think about the larger picture, like these methods would essentially go here in a like multi-stage like sort of recommender system, let's say, because very often you have a huge action space, right? These items, it'll be millions. Then you have a system that will give you a certain set of candidates, which might be hundreds, and then they go through the ranking. And so this very efficient argmax or softmax is essentially used to go from millions to hundreds in that case. Right. So I mentioned this as being a problem with sort of on-policy bandits, but it's the same in off-policy, actually. Like we do need to choose the arms essentially in each and every setting. But a second problem that you get in off-policy bandits is that the variance of all of those estimators that I've mentioned, you know, the sort of value-based ones and the policy-based ones, it very directly relates to the size of the action space, because you have way more actions, it becomes a lot more of an issue. And maybe very counterintuitively, uniformly randomly logged data does not help you here. And this is really something that I've really had to explain to many people, that like it looks like it will help you, but it doesn't. And I'll show you why. So as I said, I mean, no more very fancy math here, but just the variance of this like sort of estimator is directly proportional to the maximal importance weight, right? So the logging propensity and the ratio of the new propensity for the new policy and the logging propensity. That's really essentially it. So think we have a certain policy that we want to evaluate this pi t, and there's a bunch of different values there, you know, for different actions, and they all will sum to 1, right? And so now we have log data that's uniformly randomly logged. So we have essentially 1 over the size of the action space is the logging propensity there. So if we now want to use this data for evaluation, you can see that the maximal importance weight here is going to be 0.4 times the size of the action space. So if the size of the action space is 1 billion, this is a pretty big number, and this is probably huge variance and not usable. Whereas if you would somehow have a policy that's close to your policy that you want to evaluate, so you're taking smaller steps, then it actually looks a lot better, right? So here, the maximal importance weight is only 1.15, right, for this maximal action. And so sometimes having data that randomizes locally and randomizes around what you think is a good policy to then move to in small steps towards a better policy is much more useful than having uniformly randomly logged data. Because yes, it's unbiased, but your variance is making things useless in many cases. All right. And then finally, there's also a few like assumptions in theory that are violated that lead to bias, right? So one thing that I actually haven't mentioned, but when you're using IPS, you're making the assumption that there's a non-zero probability that your logging policy will take an action that your learned policy can take, which essentially means that we have to have a non-zero probability for any like sort of recommendation for any sort of context, which is also not extremely reasonable, right? We will have some guidelines in the system in place. And so that's going to mess up these estimators as well. And that's more likely to happen when you have large action spaces. But as some solutions in this very specific case of having rankings and recommendations, it helps if you can make structures that like structural assumptions about the relationship between your actions and your like sort of rewards. So when you have an example where we have a certain context X, we show a list of recommendations, these sort of A1 up until AL. And then we can see clicks, for example, on like all of these different recommendations. Like if we don't make any assumptions about how users behave, then whether a user clicks on the first recommendation might be impacted by the second one and the third one and the fourth one. And so we need to somehow take into account that this click observed on the first action might actually be a consequence of all of those different actions that we've taken. But we can also make assumptions saying that, well, we might just think that that's not the case. Like when a user clicks on a certain item, that's due to that item, and there's no influence of the other things that I'm really showing on the same page. But that's probably not true, right? That's probably not something that really is going to be a truthful sort of reflection of how your system is going to work, of how your user is going to work. And we can have like a few different like these sets of assumptions where you might think that, well, users browse through the list in a cascading behavior, so they'll start at the beginning and they'll go through it. So whether you get a click at a rank K is impacted by all of the previous ranks, but not by the later ranks. And so like you can make many different assumptions and start to encode them into all of these estimators to get down the variance as much as possible. But the problem is that if you make a wrong assumption, you'll be very biased, right? So like this one in the middle, very strong assumption, you'll have very low variance because you're not dealing with the ranking setup. You're just looking at it as all a sequence of like sort of fully sort of independent actions. But it's probably a wrong assumption, and so you will have a biased estimate in the end. That's essentially what I said. And so less restrictive assumptions will probably give you lower bias. So this was a relatively short setup because we also don't have much time left. But there's a great resource if you want to learn more about large action spaces, which is Yuta Saito gave a very nice tutorial at a workshop we organized at Rexus last year. It was recorded and the slides are available. And he's also been doing really great work in the last few years in this area. So if this is something that you want to learn more about, please check it out. It's really worth it. Then I will blast through this last section. I think it's 5 slides, so we will make lunch, no worries. On rewards, right? So like this is basically back to basics, right? Like we've been talking about this now for 3 hours about bandits and everything. But we've always somehow assumed the reward to be given, right? And so the reward is essentially going to be what we want to sort of pursue, like what we want to maximize. It's what we're using to learn whether, you know, a certain action is favorable or not. And there's many different ways of actually thinking about it, right? So we can think about clicks on ads, but we can also think about watch time. You know, maybe that's something that's nice. We can also just use like a certain donation amount. And so there's really a modeling decision that you have to make here, and it has big impacts. Like it's really important to think about decent rewards, because for example, if you just focus on clicks, you might get really sort of clickbaity ads to be shown very often, but you might not get a lot of money actually, right? But when you just focus on these donations, you might just have very, very sparse data because not many people donate, and it's very hard to learn from that, right? So there is a certain trade-off here to deal with. Short-term versus long-term reward is a very important thing. So, you know, short-term is things we can observe right now, like clicks. Long-term is more like whether users actually return to the system, but we have to wait for that data. So it's not great, right? So as I said, if you just focus on short-term rewards, you might get things like clickbaits. Filter bubbles are also a problem. Solutions are to optimize long-term reward directly, but it's also not that easy to do that because you have to wait for the data. And so having some method that uses both actually in some sense is often the way to go. And this is a reference that shows that when you're only considering short-term rewards, you actually have a linear sort of upper bound on the regret. But if you're both optimizing for short and long-term reward, you can actually get sublinear bounds because they can also be used to like sort of inform one another. Very often we use like for proxy rewards because long-term rewards are very hard to optimize directly because you have to wait. We can somehow figure out something that is a proxy to that event. And so like one of the reasons that it's hard to do this direct optimization is because you'll have a very low like sort of signal to noise ratio, and figuring out which of your actions led to that user like sort of coming back to the system 3 months from now is just a very, very hard thing to do. And so we can think about short-term surrogates like the diversity of sort of content consumption on a system. Things like that have in some recent papers been shown to have a high correlation with user retention. And then we'll sort of try to optimize them instead to hopefully get better retention instead of focusing on retention. The same in terms of delayed rewards. That, you know, just waiting very long is often a problem. And then certainly because you might falsely label something as a negative when it's actually going to be a positive. For example, when a user is going to come back to the system, they just haven't done so yet. Or when we've shown an ad, the user is actually willing to buy something, but they will do it when they get their salary near the end of the month. You might now think that you actually have a 0 label, but it's going to become a 1 label. You just don't know it yet. And so these are things to actually really take into account. And it's a problem, but you can do like a few solutions here in the slides as well. Very often you will have multiple objectives, right? So very often we don't want to focus on a single thing. We might have clicks, but also dwell time and also the money we're making. And then you have to resort to like multiple techniques that are going to sort of help you with this. They often boil down to like sort of scalarization, and you want to think about the like sort of Pareto front, right? So when you look at the plots, there will be suboptimal solutions, meaning that you will always be able to improve on at least one of your objectives. But like on the Pareto front, it means that like the solution that you have currently, you're not able to improve on one metric without hurting the other. So that's often what you would want to actually find. But there's often a trade-off between multiple objectives, and you have to choose where on this Pareto front you want to land. Okay, so I'm 1 minute over time, 2 minutes over time, damn. But so just to recap, we gave you, I think, a general like sort of introduction to Bandit Feedback. We went over sort of on-policy bandit, which I think is the general flavor, thinking about regrets and pure exploration. Moving to off-policy bandits, things to make it practical, large action spaces, and finished off by talking a bit about rewards. So to conclude, I mean, I think, and I'm very biased, but I think like these bandit methods are great for a very, very broad class of problems. Like they can really be used for very, very different things. But it's mostly relevant when you want to move from making certain predictions about a system to making decisions, actually, and having a system that has a certain influence on the future, let's say. Then it becomes very, very important to think about these things. I think we have presented a flavor of general classes of methods, all of these different things. And I mean, I hope that we've sort of focused on when methods work, but also when methods don't work, because I think that's mostly when very interesting research questions arise. So I hope that you agree that this has been very interesting. We would be very happy to have any feedback, so feel free to like really sort of come and tell us how bad it was, or how great it was, or mediocre, or feel free to just leave and have lunch now. But we just want to mention again that we have a website where you'll find the slides, a few notebooks, more information about us. And I will get back to this QR code in a bit, so you can all take a picture. But I also just want to mention that you've seen the both of us, but we did not do all of the work. This has been a few months of really nice work with these 6 people. And so, yeah, it's been really, really fun to work with them. And they certainly should get a big part of like all of the credits for these 300 slides that hopefully are a useful reference to you. All right. Okay, then you are all dismissed.